Okay, Ji. So as basically as I mentioned before just my Wi-Fi play a trick on myself. So let's start. Okay, basically we talk about what over here? We talk about thermal properties, right? Of solids, liquids, and gases. Of solids, liquids, and gases, right? Solids, liquids, and gases. And then we will talk about what else? What is thermal expansion, right? Thermal expansion. And then if we when have we have talked about this, we'll talk about some benefits and drawbacks, right? Benefits and drawbacks of thermal expansion, right? Okay, why is it useful? Why is it not useful? And then after that, we'll talk about some application, right? What are some applications of this thermal expansion, right? And then in temperature, we'll talk about okay, what is it, right? What is it? What is it, by the way? And then once we know what is temperature, we will talk about how do we measure it, right? How do we measure it? How do we measure it? Okay, so this is the plan, right? Then after we are done with this, we talk about some basically some calculations, some numerical, right? So numerical quantities, that is latent heat. What is latent heat? What is specific heat capacity? What is heat capacity? That basically comes under all numerical calculations or expression, right? Right. So this is the entire pattern and an entire algorithm, the table of content of the chapter, right? So yeah, let me just save it and then continue. So yeah, let's start now. So now we have the definition of thermal expansion, right? So can anyone just explain what is thermal expansion? What is thermal expansion of anything, like solid, liquid, or gases? What is it? Yes, anyone? Hamza, बताएं. Hamza, am I audible to you? Hello, Hamza. Yes, explain what is thermal expansion, Hamza. Yes, ma'am.
Sir,
Hamza, please keep your
sir,
mic ready. Yes. बताएं.
sir, if there's like if any object subject like any increase in temperature, there will be like increase in its qualities like
Hmm.
area or volume and stuff in the materials.
Okay. ठीक है. Yes, Hamza, you want to share your response? Please keep your mic active, right?
सर
Yes, Hamza.
आ रही है
आ रही है, बता रही है.
सर अगर किसी हम क्या कहते हैं मैटर या सब्सटेंस को आप हीट दो तो वो एक्सपैंड होता है
So,
सॉलिड।
how does it expand? What is the physics behind it?
सर क्या कहते हैं पार्टिकल्स की काइनेटिक एनर्जी बढ़ती है तो वो एक दूसरे को पुश कर देते हैं।
Yes, so whatever you studied in last chapter basically continues here, right? Okay, that's good. Okay, so we had relation also that the volume goes proportional to temperature, right? What was this law from the last chapter if you have watched the recordings? What is this law named? Is it Boyle's law? Is it Charles law? Is it pressure law? Is it temperature law? Yes. So this basically states कि अगर temperature बढ़ेगा आपका, so your volume also increases, right? So what is this law? Yes, Mama. Can you guess it? Is it Charles law? Is it Boyle's law? Is it pressure law or is it temperature law? I just want to
सर
see.
ये टेम्परेचर लॉ है ना।
Are you sure?
Sir, Charles law.
Yes, it is a Charles law, right? So basically, Boyle's law is saying that pressure is inversely proportional to volume. Charles law is basically this, right? The volume is right proportional to temperature. Okay, so this is the Charles law, right? And then we have pressure is highly proportional to temperature. Okay, that is what? This is what? Pressure law, right? And then we have the combined law, which was basically what? P1 V1 upon T1 equals to P2 V2 upon T2, right? Which was your homework. अच्छा, इससे मुझे याद आया कि होमवर्क क्यों नहीं किया आप लोगों ने अभी तक. There was a homework in the last lecture. So who has done that question? इसमें ये formula इस्तेमाल हो रहा था. So this was the homework in your last lecture. So who is done with this particular question? Raise your hand. If someone is done with this particular question. No one, right? So, Maeve, you basically was on winter vacations. Kindly watch the recording lectures, right? So, the first chapter of the book which I was explaining here, ये chapter हमने basically पूरा on recording किया था, right? So you have the links in the WhatsApp group. Kindly watch it in series. Slides are also on the WhatsApp group. Okay, so I will request
सर,
those who are not. Yes.
सर वो क्लास कहाँ पर है?
Hmm?
आपने कहा था क्लास शेयर करेंगे।
क्लास में करेंगे? नहीं. I said that it was.
नहीं, मैं कह रहा हूँ आपने वो ग्रुप पे लिखा था, देखना है हमें।
हाँ, वो जो, हाँ, बेसिकली आई ऑल्सो हैड टू मेक दैट अनाउंसमेंट. थैंक यू फॉर रिमाइंडिंग हमजा. So I basically was not able to take a class on Friday because I got my sore throat. So I will take this on Monday, right? If let me know if you're available on Monday. Monday around 8 p.m. Yes, around 8 p.m. कर लेते हैं.
सर मेरी केमिस्ट्री की क्लास होती है।
Fixed 8 p.m. पे होती है फिर. So what about 9 to 10? Or we can do next week also if you want. Next Saturday. ठीक.
सैटरडे को सर कब?
What about? I will post a poll. You guys can vote, right? So either Monday 8 p.m. or Saturday 5 p.m. Okay, right? So Abhi, don't worry about this. I'll give you a slot. Sorry. So again, as Hamza said, kindly please first of all complete this question. Okay, I'll post a reminder on the WhatsApp group. So again, so let's get back to the chapter over here. So let's imagine you have a solid.
सर इस इस क्वेश्चन के लिए वो स्लाइड्स भेज देंगे आप?
स्लाइड भेजी है मैंने सारी. लास्ट स्लाइड भेजी थी मैंने. लेट मी चेक. अगर नहीं भेजी हुई मैं भेज दूंगा. ठीक है. So don't worry. Let's say you have a copper rod, right? And you have particles here. We have atoms, right? Let's say atoms are this, right? These are atoms over here of the solid copper rod. Okay. So again, now what is happening over here? You are heating this particular rod, right? Let me just choose orange. You are heating this particular orange rod, right? Using a candle, right? It's a pretty good candle over here. And what happens? Let's say after 2 hours, the size of this rod becomes this. It becomes this. Let me choose this one. It becomes sort of this, right? So what has happened? Basically, when you basically gave enough energy, when you heated up the entire copper rod, what happened? These particles started to vibrate, right? These particles started to vibrate rigorously. So what happened? So increasing temperature did what? It basically increased the kinetic energy. It increased the kinetic energy, right? So as soon as the kinetic energy started, so the particles collision rate, particle collision rate increased, right? And that basically increased spaces between atoms. And what is the result of this? The result is that the rod has expanded, right? The rod expands, right? So this is the entire algorithm. So that's how basic thermal expansion works. So this is for solids. Similarly, this thing can be applicable. The algorithm, the steps are same for liquids and gases also, right? All right. So this is for solids. So same logical phenomena, same physics, basically rules that is 1, 2, 3, 4 basically are applied, right? So same thing happens in other states of matter, right? So if this is clear, give me a thumbs up. Okay, clear to me, if clear to Mama. Okay, clear to Hamza. That's good. So now let's move on to the relative expansion of solids, liquids, and gases, right? So now we're comparing that how much solids expand as compared to liquids, and how much gas expands as compared to liquids, right? So we're gonna have a comparison over here, right? So yeah, before starting this, I want to ask the question from you guys. Okay, what do you think? Which state, gases, liquids, or solids, which one expands the most, and why? Yes, quickly.
सर गैसेस.
Why, Hamza?
सर गैसेस में ज्यादा स्पेस होती है ना, तो वो और ज्यादा दूर जा सकते हैं एक दूसरे से. वैसे ही वो
Perfect.
ज्यादा उनके पास काइनेटिक एनर्जी भी होती है.
जबरदस्त. ठीक है, that's good. ठीक है. So that's an spot on answer. So again, Hamza is saying कि sir, अगर let's say, let me just insert a blank slide over here. Let me insert a blank slide. Let's say this is a container, right? Or let me just say कि let me draw a balloon. बहुत आसान होगा. Let me draw a balloon. ठीक है. And in this we have gas particle, right? ठीक है. So what happens? Let's say if we heat it up, right? Let's say we are heating up with a candle, right? Candles are here. Candles are here, right? These are the candles, and we are just heating it in such a way that the balloon does not explode, right? It's just slight heating from the surrounding, right? Okay, so what happens over here? Again, as soon as these heat energy basically travels through this balloon, so this will basically increase the temperature of the inside of the balloon, right? And that energy would basically cause the particles to vibrate, right? They will basically move way fastly, right? Because they have more spaces between each other, and they can move rigorously, right? So again, what happens? So as you increase the temperature, this again increases the kinetic energy of the particles, right? So what happens? Particles travel faster as compared to solids or liquids, right? Solid or liquids, okay? And since due to more spacing, due to more spacing, particles, the particles of gases basically goes further apart, leading to greatest expansion, right? Greatest as in K, more than solids or liquid, right? So this is basically what is happening, right? So just what is the thing which is causing the gases to expand more? The spaces, right? So they have more spaces between the particles as compared to solids or liquid, right? In solids, the particles are jammed together, right? They're paired together in a sequential manner. In liquids, the particles are slightly basically displaced, right? Such that they can move freely, but not at a huge pace, right? But in gases, ओके, एक और चीज है हमारे पास, फोर्सेस ऑफ अट्रैक्शन भी क्या थी हमारे पास. द फोर्सेस ऑफ अट्रैक्शन इन सॉलिड was stronger the forces of attraction in liquids, and the forces of attraction in gases, right? So forces of attraction क्या है हमारे पास कि what is the force that is basically keeping these neighbors together, right? These neighbors together. So the forces in gases are the weakest, right? That is also the reason that they can move freely, and they can expand easily, right? So this is the reason that the gases can expand most as compared to solids and gases, right? Does that make sense? If yes, thumbs up. Makes sense to me. If Mama and Hamza, this is just the summary of what we have discussed right now. The particles in a liquid are further apart, less ordered, and are more mobile than in a solid. So the direction between the particles is less, and expansion is easier for liquids than solids. Right? Liquids typically expand about 5 times more than solids. Right? This is just a rough estimate. Okay, they have carried out experiments and they have basically taken an average, and the average was coming out to be five. That it was 5 times more compared to solids, right? However, in gases, the interaction are few because basically they have very weak forces of attraction between the particles, right? So because they are far apart and they move very quickly, right? This means that they can expand more, right? So gases can expand 20 times more than liquids. ठीक है? Just imagine कि liquids can expand 5 times more than solids. Gases can expand 20 times more than liquids, right? So these figures indicate that gases expand much more readily than liquids, and liquids expand much more readily than solids. Again, if I want to write down the summary of this, that is as follows: that expansion of gases are greater than expansion of liquids, and expansion of liquids are greater than expansion of solids. Right? If you increase the same temperature, right? Let's say if you increase the temperature by 20 degrees Celsius in the same experiment, so you will have these values, right? And by how much? Liquids can expand 5 times more than the solids for a given temperature. ठीक है. And liquids, gases can expand 20 times more than the liquids at the given temperature, right? These are just estimates and these are just experimental results, which basically dictates that how is expansion linked together in different states of matter, right? So again, now we have learned what is expansion. Now let's learn some uses of expansion, right? So these expansion are not basically all the time. Uh, it's not basically, let's say, not useful. It's useful sometimes also, right? So before just starting this section of the lecture, I just want to ask a question. Can you give me an example of the use of expansion in real life, apart from the example given in the slide? Any example, it can be anything. Just think about, you can think about some,
सर
yes, Hamza.
सर वो ब्रिजेस में वो थोड़ा सा गैप रखते हैं जो हीट से एक्सपैंड हो जाता
Perfect,
है मेटल
perfect, right? So whenever you're going across a bridge, right? So you might have seen this, right, Hamza? That's good. So let me just insert a blank slide. So let's say this is the bridge, right? This is a bridge over here. And in bridges, you might have seen some basically some breaks like this, right? Let me change the color over here. Let me say, you might have seen some sort of gaps between the different parts of pole, right? Bridges. So these have some basically spacing in between, right? And on the top we have metal, right? And after some spacing, you have again another metal piece, right? So what are these for? So basically in summers, what happens, right? Usually in Karachi, what happens in summer, Hamza? Temperatures around 37 to 40 Celsius, right? And in winters, right now, we can basically can confirm this. Your temperature is around 21 degrees Celsius, right? And it goes to 9 in the night, right? So once you go from winters to summers, what happens? The metal basically faces expansion, right? And these expansion basically, if there are no spaces between these bridges, right? This is a bridge over here. So what would happen? These might basically break, right?
ब्रिज कोलैप्स हो जाएगी
These might cause some cracks on the bridge, okay? And let's say if a heavy material, heavy car, let's say goes through this, they might basically cause a dent or a basically a destruction over here, right? Let's say the bridge is over basically some certain height, right? Height of let's say 10 meters below the ground. And let's say there's a crack over here. These might basically cause some weakening of the structure, right? And God forbid, there might be some harmful scenario also, right? That is why we have some spacing over here. That's good. So now imagine this is an axle, right? So what is an axle? It basically is a gear in gear wheels. Okay, so your wheels are moving. Okay, how do they move? They have some gears. Okay, so if I zoom in over here, you can see okay, what are these? So there's a rod in the center, right? There's a metal rod in the center. That is this. Okay, metal rod. And then you have some gears over here, right? You can see some gears over here. Sometimes what happens, you can see the diameter over here, the circular area over here, right? So they want to basically fit these gears on these rod, right? So sometime what happens, they are not able to go into it, right? They're not able to go fit into it. So what do they do? So basically they cool down this rod, right? They cool down this rod using nitrogen, right? So nitrogen, liquid nitrogen. So liquid nitrogen is around at -100, around roughly around -100 degrees Celsius. So that does what? That basically causes the spatums in this rod to contract, okay, and such that they can easily fit the rod, the basically rod contracts. So if let's say the diameter of this particular gear was smaller, so it can easily fit into it, and they basically then take this rod into room temperature, and this basically causes the rod to grip the gears pretty strongly, right? So that the grip is pretty strong and they fix into the rod perfectly. Okay, because these are inside the wheels, and if they are slightly weaker, slightly loose, they might cause some distraction, right? The motion. Does that make sense? If yes, thumbs up. Quickly, I want to move on. Okay, makes sense to me. If ठीक है, this is just a summary over here. ठीक है, so axles and gears are major components of clocks, or let's say cars also, right? So what happens? They shrink the rods and freezing liquid nitrogen, which is at exactly -196 Celsius. Okay, and so you can slip the gears into the rod, and on regaining normal temperature, the axle expands to give a very tight fit, right? So that the construction is pretty strong. Okay. Then compare this. Now you might have done this on in your kitchen with your mother or let's say your sister. Okay, so you might have a, let's say, jam bottle over here, and it might have a lid, right? It might have a lid also. Let's say this. Why is this happening to me? Yeah, yeah. So sometimes in winters it might happen. Okay, you cannot open this lid easily, right? This is the lid over here. You might not able to open the lid easily. Okay, so how do you basically solve this issue? Can anyone explain their personal experience that they have used to basically open a lid which is jammed in winters or any season? Yes. ठीक है, so मैंने क्या कहा था, basically I basically faced this personally. So I basically went into my kitchen, right? And I went into my basically the sink, ठीक है, the wash basin, and I had a tap over there which was basically giving me hot water from the electric geyser, right? So I did what? I basically, the water was coming here. I basically took my jam, jam bottle, right? And I basically did this, right? I just basically washed my lid with the hot tap water, right? So let's say this is your lid over here, right? And if you basically heat up the lid, what would happen? There would be thermal expansion, right? So this would basically become sort of thermally expanded, right? And thus it can basically be easily opened. So because once you have heated it, so वो thermal expand हो जाएगी and it becomes easier to rotate and take it. This is just a real life experiment, a real life example, which is pretty common in kitchen, right? So again, a tight metal lid can be removed from a glass jar by immersing the lid in hot water so it expands and loosens, right? Expansion of a liquid of a glass can be used in thermometers to measure temperature, right? तो हम देखेंगे अभी in temperature how does thermometers are designed and how does it gives us exact value, right? So expanding gas drives the pistons in the engine of a motor car, right? So this is just imagine this is just giving you some examples of applications of expansion. So in a car, what happens basically? Let me just give you a quick summary. होता क्या है? So let's say you have a car, right? A Bugatti here, So in this car, you have an engine, right? So you have engine. So this engine is basically doing what it is doing combustion. It is burning the fuel of the petrol to produce energy, and that basically produces carbon dioxide, right? So that gas basically moves the pistons, right? So that piston basically moves your wheels, right? That is how the entire the combustion in the car works, right? This is again uh, telling you can gas expands and causes the pistons to move, and this is just a useful application of expansion. Can you give me a non-useful application of expansion? Okay, where expansion is harmful for us. We have seen all the good ones, right? So what are the bad ones?
Pollutions of the gas, like you showed the example of the car right now.
Mm-hmm.
So like the gas is spreading.
Okay. So okay, ठीक है. So anyone else? उसके अलावा close, close. What is the drawback of expansion? Let's say if we have something thermal expansion, right? So is it harmful also, or is it useful all the time? ठीक है. So let me just give you an idea. So so basically you might have seen these electrical towers, ठीक है, power towers, right? So three, one, two, three. You might have seen these, right? So these are basically connected together, and these are sort of like this. Let me just make one of it, just to give you a clear example, an idea. Okay, so let me just give you one of them, just to give you an idea. कि होता क्या है. So you might have seen these. Okay, so have you seen these power
यस
towers,
सर.
right? You might have seen that they are saggy, right? They are saggy in basically in summers. Saggy means that they are basically like this, and in basically this is summer scenario over here, and in winters the opposite happens. So in winters you might see this, you might see this, right? So is it useful or not useful?
सर क्या फर्क है इनमें?
Can you see these are wires? These are power wires. These are the cables, right?
ओह.
Carrying the power, right? So you might have seen this. These are basically power towers, which are carrying power from the power station, right? This is a power station over here. So this is basically bringing power from power station to your houses, right? So they are designed in such a way in summers they can be like this, and in winters they can be basically be because in winters what happens? The temperature is around 10 degrees Celsius, and what happens over here? The basically solid wires contracts, right? Contraction occurs. So the length of the wires can basically become this. And in summers, there again the wires are made up of copper, right? Copper is a metal, and metal has thermal expansion and contraction property, right? In summers, the temperature is around 40 degrees Celsius, right? So it basically does what? It basically thermally expands. So expansion takes place. So what is the drawback of this? You have to basically use longer wires. Does that make sense? Does that make sense? Because you have to use longer wires to summer में actually ऐसे हो, and using physics, these wires basically contracts and becomes and takes the shape, right? Does that make sense? If yes, give me a thumbs up. You just observe this, right? Whenever you're going through a road or a let's say or an area where you have too many power lines on your top, just observe this in winters and summers, right? We'll see this property because now इसका drawback क्या है? They have to use more copper wires, longer copper wires. So longer wires are required. ठीक है? So it basically does what? It increases your cost. Yeah, it increases your cost, right? So Umema, is it clear?
No, sir, I still have confusion.
Okay, so it's pretty simple. Uh, what are wires? Wires are made of copper, right?
Yeah,
Okay. So when you heat up a copper, what happens? Does it expand or contract?
expansion.
Hmm. Let me just insert a slide. So let's say you have this copper wire, okay, and you basically are, let's say this is inverter, right? Inverters, the copper basically length is around, let's say it is around 1 meter, right? So in summers, right? Let's say if you reach summer, so what happens to this rod? This rod basically becomes longer, right? Let's say it becomes 1.2 meters. So for designing the actual wires, you would have to consider the maximum size of the wires required, right? Because you would need at least 1.2 meters to basically join 2 points. Okay, so you have to basically you have to place extra wires, right, in the power supply cables. So these are power supply mounts over here. These are called power towers. So basically in this they are carrying power through cables, right? So you have to use some extra amount of wire just to basically put in this particular phenomena that inventors the wire will shrink, right? If you already placed wires like this, let's say if your wires are already very short, okay, let's say if your wires are already like this, so in winters, they will basically contract further, and if they contract further, they will basically break, right? Does that make sense? So you have to put in extra length of the cable such that when they shrink in winters, they basically stay in contact and they do not break, right? So this is again a drawback. You have to use extra wires. You have to basically increase your cost. ठीक है, I hope it makes sense now. ठीक है. Now we have some very interesting side of the chapter, that is an again application of expansion, that is a bimetallic strip, right? So it is present in your air conditioners right now. It is present in your refrigerators right now. It is present in your fridges. Okay, it is present in your fire alarms. It is present in your uh let's say thermostat which you have in your university or schools, which basically automatically sets your temperature, right? So can anyone explain that how does this work? How does the some bimetallic strip work? How does a bimetallic strip work? Yes, anyone? Give me a guess quickly. The time is getting closer for the class. Quickly, you should give me a guess quickly. जो कलर तो सला तो सही है. Yes, Mama, give me a guess. A quick one.
सर ये
I don't
स्ट्रिप जो
know this
है,
one.
Raise your hand and answer. Yes or no बोले.
सर इस स्ट्रिप में अगर क्या कहते हैं एक्सपैंड होता है तो ये ऊपर की तरफ होता है लेकिन नीचे की तरफ नहीं होता.
Are you sure?
सर इमेज के हिसाब से तो ऐसा ही है.
नहीं. अच्छा नहीं चले. Bimetallic strip क्या होती है? Bimetallic means के we have two metals. Bi means two, right? And metallic means metal. So a strip which has two metals is called a bimetallic strip, right? So this is a bimetallic strip over here. It has a copper metal on the top and an iron metal on the bottom, right? So again, so it has different expanding properties, copper, iron. So copper basically expands more as compared to iron at a given temperature. Okay? So this basically expands lesser as compared to copper, right? At a given temperature. So this is basically utilized in a very smart way to create some circuits, right? So what happens if you heat this particular rod, right? So again, since copper expands more, you can see the expansion of the copper is, let's say this was the length of both the rods initially before heating was 1 meter, right? And after heating it, so basically since copper expands more, you can see that the copper has a greater circumference, right? So it has expanded more. So let's say this is basically 1.1 meters, and the inner circumference of the iron, which by which it has expanded, is basically 1.05 meters, right? I hope it makes sense. If the radius of circle is smaller, the circumference is also small, right? The arc length is smaller. Let me just give you an idea using an arc idea. So let's say this is your arc, right? And if I basically increase my radius, the arc length the arc length becomes more, right? This is S2, this is S1, this is theta. Okay, and this is the radius 1 of the arc 1, and this is the radius 2. So if your let's say the rod is further away from the center, okay, so the arc length is greater than the arc length 1, right? Just imagine the expansion of copper, the rod which is on the top, which expands more, will basically have a greater expansions compared to the rod which has lesser expansion. Does that make sense? If yes, thumbs up. ठीक है, जस्ट सिंपल मैथमेटिक्स ओ लेवल्स की पढ़ चुके हो हम लोग. Yes, Maeve. It's clear to Hamza, it's clear to Mama. Yeah, it's clear to me also. That's good. So again, this is just saying if equal length of two metals are combined together, such as copper and iron, so they cannot move separately. They are fixed together by strong, let's say, joints. So they form a bimetallic strip, right? Which is this, right? And when heated, copper expands more than iron, and this basically allows the strip to bend, right? So it bends in a sort of this arc method over here, arc over here. If they have expanded equally, the strip would have stayed straight, right? Let's say if they were expanding at equal rates, so they would basically expand in this direction, right? Equally, right? So it would remain straight, right? I hope it makes sense. So now, what is the application of this? This is the application one of bimetallic strip. Application one of bimetallic strip, which is fire alarm, right? So how do we use this in fire alarm? Let me just take you into the circuit diagram. So we will do electricity in detail, and my major of bachelor's is electrical engineering. So I hope that would be interesting, right? So let's go over here. So you have a battery over here, a battery. You have a battery over here, right? Let me make it a cell since it is single source. It is a cell over here. This is the electric bell, and this is basically the bimetallic strip, right? So what happens basically? यहाँ पे आप heat energy इसको दे रहे हैं, right? As soon as this basically this switch is on, this heat is basically turned on. As soon as this basically heat is turned on, the heat is turned on. So what happens? What happens basically? You can see okay, this is copper over here, this is copper over here, and this is iron over here, right? How would this bend? This would basically bend in this direction, right? Like this. This would bend in this direction. Oh my God. Right? This would bend in this direction. So this would basically go up, right? And this is a contact sort of metal strip, right? So as soon as it goes up, it forms contact with this particular metal, and the circuit is complete, right? The circuit is basically complete, and the current flows, right? As soon as the current flow, this basically electric bell gives you a sound, right? Just like in your school, when your period is over, there is an electric bell, right? This is a circuitry inside the electric bell. They use a bimetallic strip over there. As soon as your principal or your any in charge basically presses the button, this basically turn on the small heater over here, which heats up the bimetallic strip. As soon as it is heated on, this basically connects the entire connection with this contact point. This allows current to flow in the entire circuit, and this basically turns on the electric bell. And as soon as you turn off the button, the this rod cools down. It basically goes back to straight position, and again the contact breaks since there is no complete path for the current to flow. So the basically the bell would turn off then, right? If it is clear, thumbs up. Clear to Mama. Okay, it's clear to Maeve. create home, right? This is a simple application of fire alarm, right? अच्छा, यहाँ पे that was an example of school. So this is an fire alarm. So obviously जब यहाँ पे हीट होगी, जब फायर होगी तो हीट एनर्जी प्रोड्यूस होगी. तो जब हीट होगी तो हमारे पास बायोमेट्रिक से ऑटोमेटिकली बैंड हो जाएगी एंड दिस will complete the circuit. And as soon as there is no fire, this rod stays straight, right? Yes, Hamza, question?
नहीं सर.
Okay, good. So again, heat from the fire makes the biometric strip to bend and complete the electrical circuit, and the alarm bell rings, right? So biometric strip is also used in this way to work in flash and direction indicator. So being warmed up by an electric heating coil won't ठीक है. So basically when you keep an indicator in a car, so it basically turns on and off, right? So how does it turn on and off? So inside your circuitry you have a certain small heater, राइट. तो उसके अंदर छोटी सी हमारे पास बायोमेट्रिक स्ट्रिप होती है विच बेसिकली constantly basically converted into this shape and this shape, right? So when it comes into this shape, your indicator turns on, and when it comes over here, it turns off, right? So this repeats in a sequential way to basically give an indication lighting signal, right? Okay, जी. Then we have thermostat, right? So I will give you guys this as a homework assignment so that you guys read the slide before the lecture also. This is a homework. So I want precaution against expansion. Now we have learned how is it useful, right? We have learned it's pretty useful throughout expansion, but it can also be basically harmful for us, right? So can anyone give me a drawback of thermal expansion in real life? Where it can be dangerous for, let's say, the people or for the environment, or let's say in practical applications. Can anyone give me an example? You can guess around.
Sir, when
Mm-hmm.
sir, can I tell?
Sure.
Usually, like I guess, जब ट्रेन चलती है तो जो रेलवे ट्रैक होता है ना वो गर्म हो जाता है तो उसकी वजह से गैप्स आ जाते हैं इन द रेलवे
Yeah.
so it makes it hard for the train to go
Yeah. ठीक है.
when heat
So,
heats up.
Zabardast. So when the basically railways were getting established by British, ठीक है, in your 19th century. So this was the problem which they faced, right? They basically placed straight like this. They placed straight rails, ठीक है, without any gaps, right? Like this. These are rails. So what they basically faced in summers, they basically bent. They basically had a bent over here, sort of. Was they basically were expanding, right? So this basically can cause the rail train to basically topple off, right? So now what is the solution for that? They have basically introduced some spacing here, right? Which you can see, okay, these are spacing over here. So when they expand in summers, they basically they go in this direction, right? So that they can counter the effect of expansion in summers, right? In winters, there is no issue. It basically fits right as it is designed over here. But whenever you basically, let's say the train is going in this path, right? And there are two basically connections over here, right? One is going straight and one is basically connecting you over here. So let's say the train is coming from here and the train wants to basically, let's say, go in this direction. So again, they have some connections in such a way that they have some small gaps so that they can create a smooth transition towards the left turn, right? And you might basically feel a small jerk when the train changes the tracks. Has anyone traveled through train? I believe most of you should have. If yes,
Sir, I have.
raise your hand. Those who have traveled through train. Yes, quickly. I want to आगे lecture बहुत ज़्यादा है. Those who have traveled through train, raise your hand. Okay, what the has only. Mashal, are you able to listen to me, or Hamza and Maeve? I guess you guys are all chilling out. I was in the lecture. Yeah, Maeve is here. Hamza? मुझे लग रहा है Hamza and Mashal are having their dinners and they're just keeping the laptops and the mobile phones on, right?
सर मैं
For the
हूँ.
sake of participation. Hamza है. Okay, Hamza is here. Mashal, you're back after a month. Is your internet back? Okay, चलें बाद में बात करते हैं. So then let me just quickly go through the content here. So when matter is heated, it expands. When it cools, it contracts, right? It is just the thermal property which you have seen, right? होता क्या है? So if the changes are resisted, large forces are created, right? which are sometimes useful, but other times it is basically harmful experience over here. Let's say if there was no spacing in the railway track, the track might become curved, right? It might cause basically train to topple down, right? This is a harmful effect. Similarly, if you have wires, the electrical wires here, which you have seen in the last slide, if the wire was straight and let's say you have designed the wire to be straight in summers. Let's say now the winter comes and the temperature drops. So this basically should lead to contraction of the metal, right? So that might break your wires, right? This is another drawback over here. So that's how we need to consider thermal expansion in designing any application. Okay, the real life applications over here. So gaps are left between lengths of railway lines to allow for expansion. So again, they make a clickety click sound when the train passes through them. And okay, yeah. Another one is basically the pipes. Okay, the metal pipes which you basically have in your homes. So if you have sort of a connection over here, these are sort of wide connections over here, which basically connects the two pipes. So they have some spacing in between, right? So this basically allows for the expansion of the pipe during summer, right? So again, you can just go to your, let's say, you can just check where are your pipes in your homes. Just try to disconnect one and check case I want to be. Whenever you, let's say, parents are saying, "What are you doing?" Just say, "Okay, so Khuzaima wanted us to basically verify the thermal expansion, right?" It should be the case over here. If you have metal pipes in your homes, okay, usually we have plastic and PVC pipes, okay. Okay. Now, since we have learned the theoretical stuff, it's basically now we should start going towards measuring temperature, right? So now we know what is temperature, what are thermal properties of different states of matter. Now we should know basically, first of all, what is temperature and how do we measure it? Can anyone tell me what is temperature of a body? What is temperature of a body? जल्दी से बताएं. You should answer quickly, जल्दी जल्दी. Is the hand answer? What is meant by temperature of a body? Yes, बताओ.
So the temperature of a body is like how hot or cold the body is.
Yes. ठीक है, that is as simple as it can be, right? Next सवाल would be from Mashal. ठीक है. If Mashal does not reply, I would ask Hamza. ठीक है, तो stay ready. So, what is temperature of a body? Let's say I have this is Hamza standing over here, right? And Hamza, let's say use your thermometer to measure the temperature of a body, right? And it comes out to be, let's say, 37 degrees Celsius, right? That is the normal temperature of a human body, right? So now this is basically telling okay, what is the average temperature of the entire body, right? It is telling you what average temperature of the entire body, right? Okay. So what is basically temperature? Let's define this further. Temperature is just basically a measure of how hot or cold a body is, right? That is it. Okay. So it is basically measured in Celsius. Okay. This temperature is measured in degree Celsius, right? And yeah. So this is just temperature of a body, tell us how hot the body is, measured using a thermometer, okay, usually in degrees Celsius, right? Acha, so now we know what is temperature. So you already have learned that now we use thermometer to basically measure temperature. So can anyone tell me what is a thermometer? If you want to talk about its construction, that is also okay. If you want to explain okay, what is it, what is it used for and how does it work, that is also okay. Hamza, explain this. What is a thermometer? Please open your mic and get closer to your
वो
mic.
हमारा
Hmm.
हमारा बॉडी टेम्परेचर चेक करते हैं ना।
Nah, I can also measure temperature of a liquid also. It doesn't matter.
तो
What is it?
जी जी वैसे ही किसी का भी टेम्परेचर चेक।
So, how basically इसके पॉइंट्स क्या होते हैं, कंस्ट्रक्शन कैसे होती है इसकी थर्मामीटर की?
तो इसके अंदर एक लिक्विड होता है ना जो हीट से एक्सपैंड हो जाता है, वो एग्जैक्टली उसी टेम्परेचर पे एक्सपैंड होता है, जिससे जो जितनी हीट उसको रिसीव हुई थी तो वो टेम्परेचर लेबल हुआ होता है, तो वो डिस्प्ले जो होता है वो टेम्परेचर होता
So usually what substance do we use in thermometer?
है। मर्करी।
Perfect. Is it safe to eat mercury? Can you eat mercury?
नो।
Ever taste of it?
नो।
No, right?
नो। नो।
Achha, mercury is the only metal which is liquid at room temperature, right? So inside this particular thermometer, okay, first of all, this is called liquid in glass thermometer, right? Because it has a liquid inside it, okay, and the tube is made up of glass. Okay, it's called a liquid in glass thermometer, right? Liquid in glass thermometer, right? So, and the substance which is used inside this is mercury, right? Okay. So, up, let's say we have created a thermometer. We want to find okay, what we want to find basically 2 points in the thermometer. That is the boiling point or the steep point or the ice point or the freezing point, right? This is also known as boiling point, boiling point, and this is also known as freezing point. Okay. So whenever you want to basically, let's say you have a device ready and you want to mark okay, this is 10 degree, this is 20 degree. Okay. So how do you mark it? So uska hota hai procedure. We have algorithm for that, right? So the first step is basically you want to find the freezing point, right? And how can you find this? You can place thermometer, you can place it in ice cubes, right? So when you place it in the ice cubes, when the reading settles, let's say it settled over here. So this is the point that is called 0 degree Celsius, right? Because ice has temperature of 0 degree Celsius, right? Then you basically find the boiling point. Okay? Boiling point as in I want to find the mark at which the liquid settles. So I'm going to basically place it in boiling water, right? Place it in boiling water. This is a practical exam question. ये पूछते हैं आपसे कि how to mark it, right? In boiling water. And then when your reading settles down, let's say your liquid settles down to this particular height, that is basically your 100 degree Celsius point, right? Okay, so this is the two steps to the true point which you have discovered now. Now you want to basically find out, okay, now how do you mark the remaining points, right? So you know कि इसकी कुछ length होगी इसके बीच के और इसके बीच में. Let me just mark it here. You know okay, the difference between this is basically 100 degrees Celsius, right? And you can use a scale to basically mark okay, what is the length between these 2 points also, right? You also find using scale the delta L, right? Delta L. That should be in, let's say, centimeters. So if you want to find remaining points, you can do what? You can just basically find okay, what is per degree Celsius length, right? Let me just, what is per centimeter? Not this, per degree Celsius. Let me just fix my degree sign. So you can do what? You can do 100 degrees Celsius divided by delta L, right? That would give you K. Let's say this length comes out to be 20 centimeter, right? So that would give you that you have 5 degrees per centimeter, right? So you can mark your the remaining values. Let's say this is 10 degrees, this is 20 degrees, ठीक है? So 1 centimeter के लिए it basically travels 5 degrees, ठीक है? So this would be basically 2 centimeters, ठीक है? So you can use a scale to basically mark the remaining degree points here. So if this part makes sense, give me a thumbs up. About construction, Mashal is here too. Okay. If this is clear, give me a thumbs up quickly. It's clear to Hamza. It's clear to Mashal. It's clear to Mehma, Maeve, Varda. Varda, clear है?
सर मुझे मैं थोड़ी डिस्कनेक्ट हो गई थी, तो आप वापस रिपीट कर सकते हैं?
Okay. So basically, where did I lost you?
आपने शुरू ही किया था ये वाला पार्ट।
So let's say you have a thermometer. You basically have two steps, well, okay, three steps here, right? That is the third step. So first of all, you find the freezing point, okay, of the thermometer. You will basically just place the thermometer in ice cubes. So when this basically liquid settles to a certain height, that will be your freezing point, right? आपने उसको मार्क कर लिया on thermometer. Then you put the thermometer in boiling point, oh sorry, boiling water. So obviously you know that boiling water temperature is 100 degrees Celsius. So when the temperature, when the again the liquid will basically start to flow up and will basically fix to a certain height, right? And that basically gave you the 100 degrees Celsius point. तो आपने वो mark कर लिया on thermometer. Then you know okay the difference between the steam point and the ice point is 100 degrees Celsius, right? Because what is 100 minus 0? That is 100, right? And you can use a scale to mark कि इसकी length कितनी है, how many centimeters is basically the difference between the steam point and boiling point. Then you can you can just basically mark the remaining points by using this method. You can just divide 100 degrees Celsius by the length. Let's say your length was 20 centimeters. What is 100 upon 20? It is 5 degrees per centimeter. That means कि this, let's say this was a 10-degree point, right? Right. So from 0, it would be basically 2 centimeter up. Then you can mark the remaining points on the thermometer, and then that's how you basically tune, or let's say mark the remaining points of temperature on a thermometer. Okay, does that make sense? Or the okay, good. Now this is getting real now. ठीक है, अब हम लोग सिर्फ पहले तो बातें कर रहे थे, that was basically application based and some property learning, right? Now we're gonna basically start converging to a formula, then we solve some questions. So before starting, we have specific heat capacity over here, right? So this is basically going to lead to a formula that is going to be this. That energy of a system, okay, is going to be mc delta T. Over here, we have how many factors here? We have m is mass, c is specific heat capacity, which we will learn what is it, and delta theta is the change in temperature, and delta is E is the change in internal energy. So then we solve some questions. Okay, so pay attention now. So first of all, we're gonna start with the idea of internal energy over here. Okay. So we're gonna learn about some internal energy part. Let's say we have a gas, right? This is a container. This is a gas container here. And we have gas particles here, right? So if I say, okay, the particles obviously are moving with certain velocities, right? They're moving here and there with certain velocities, right? V, V, right? So if they have velocities, okay, they should have kinetic energy, right? And how do I compute kinetic energy? The kinetic energy can be computed using the following formula, that is half mv square, right? So if I basically want you guys to basically say, and is has a unit of the SI unit of kinetic energy is joules, right? That is energy. The kinetic energy is joule. So if I want you guys to basically answer this question, what is the energy stored in the gas? So what would you answer for this particular question? Okay, if I say okay, you have this gas, and if I ask you a question, okay, what is the energy store form that is available in the gas? What would you answer? Hmm. जल्दी से बताएं. Just want to guess a term over here. Can be wrong, can be correct. No worries. No one is judging you. We're all learning over here. Hmm. What is
Sir, it would be half mv square.
that is
The
kinetic
kinetic
energy.
energy, right? So
Yeah. So internal energy basically of a system refers to kinetic energy. Okay, because the particles are moving with a certain velocity and speed, and if they have speed, they have kinetic energy, right? And kinetic energy is measured in joules. So if I say internal energy, why is it internal? Because it is the atomic level energy, right? Okay, if depending upon the particle motion, the kinetic energy is possessed by the entire gas. Okay, so the internal energy is basically is referred to, is getting referred to what? The kinetic energy of the system over here, right? The kinetic energy of the system. Okay. So this is just stating that thing over here. So when object is heated, the temperature rises, right? And you know okay, when temperature rises, the internal energy of the object increases. How? Let's see. So when your temperature increases, then your velocity speed of the particle motion increases. If your speed increases, you have kinetic energy proportional to velocity speed squared. So if your speed increases, so your kinetic energy also increases, right? Then we just stated over here that internal energy, that is IE, is basically equals to kinetic energy of the particles, right? So if your kinetic energy is increasing, so does your internal energy of the system increases over here. So that is what is written over here, that when your temperature rises, that causes the the kinetic energy increment, and that basically links to the increase in internal energy of the system over here. And temperature and energy are scalar because they don't have direction. Just it is very important over here, okay? Because they only have unit and magnitude, right? So they both are scalar quantities. Any questions till now? Okay, ठीक है. Good. It's clear to Hamza. What about the rest? I believe it is clear. It's clear to Mem also. ठीक है. So again, this slide is also stating the same thing. Kinetic energy regards temperature as a measure of average kinetic energy of the particles. The greater kinetic energy, the faster the particles move, and the higher the temperature of the body. Increasing the temperature increases its internal energy because the kinetic energy of all the particle increases. That is just what we had discussed here. Okay. So these 4 points are the summary of these two slides. Okay. Thermal energy and temperature. Okay. So now I want you guys to uh, think about this. Let's say we have this. We have a C. Let's say we have a C here. And this is the land. Let me choose different color. Where is the brown color? Here it is. And this is the land, right? The temperature of the land, let's say this is, I'm talking about the morning here. Okay, it's pretty hot here, right? The sun is shining. Temperature of the land at this particular time of day is, let's say, 30 degrees Celsius. And this is temperature of land. The temperature of sea is basically 15 degrees Celsius. Okay. So from your geography classes, so where should the wind flow? Should it flow in this direction or should it flow in this direction? And I want someone to answer and explain why. You have learned this before, and you have also appeared in your O2 exams, so you should know this phenomenon. Where should be the direction of the wind? Yes. Achha, not let's not talk about the wind. Let's talk about just energy transfer. How would the energy transfer? Should the land be basically transferring energy to the sea, or sea is going to transfer energy towards the land? जल्दी से हमजा आप बताएं. Quickly, we have a minute left in the meeting.
शायद सर लैंड से सी होगा.
Can you repeat?
लैंड से सी पे.
Land to sea, Mashal is saying land to sea, right? Because thermal energy transfers from higher temperature region to lower temperature region, right? So this is basically direction of energy transfer, right? Because the land has more high energy particles, so those energy particles basically can move towards the low energy region, lower temperature region, that is this, right? So the energy would basically flow from the land towards the sea. Okay? And hence in the morning you have land breeze also, right? Do you recall this land breeze? What is land breeze, Hamza? What is land?
हवा.
हवा. ठीक है. So land breeze basically in the morning. So in morning the sand becomes hotter more and faster as compared to sea. So the wind basically flows towards what? That basically the temperature, the energy transfer is basically from a region of higher temperature to a region of lower temperature, right? So you can see that the land is at high temperature right now and as compared to the sea. So the energy transfers from basically land to the sea, right? This is the principle of energy transfer, right? If it is clear till now, give me a thumbs up. Okay, it's clear to everyone. Let me basically call in. Okay, maybe here they are joining. Okay, let's move on. Okay, so just to skim over here, we have already discussed these points. So it is important not to confuse temperature of a body with the thermal energy, right? This is pretty important here, right? A temperature is just basically a measure of how hot or cold a body is, right? Thermal energy is basically dependent upon the kinetic energy of particles, right? Right? This does not, kinetic energy basically does not tell the temperature, right? It does not tell the temperature. Temperature is measured in Celsius and the energy is measured in joules. So उसकी units be different, right? So don't just confuse the temperature is same as the thermal energy, right? Okay. For example, a red hot spark from a fire is at higher temperature than a boiling water, right? So let's say if you have a boiling water pan here, right? And let me draw a boiling water. Okay, let's say this is the boiling water here and it is basically the pressing. Also, this is basically water at 100 degrees Celsius, right? And let's say you have a hot rod wire, and usually the hot rod wire is in form of yellow, orange color, and you have red sort of red hot spark. Let's say let me just shade this with red also. It's sort of orange red, right? So let's say there's a spark, right? Spark. Let's say it is electrical spark here. So the energy, the temperature, right? So the temperature can be greater, right? Let's say this temperature of the spark is let's say at 600 degrees Celsius, right? So you can compare, you can see the temperature of this spark is at 100 degrees, 600 degrees Celsius, but the water is at 100 degrees Celsius, right? But if I talk about the overall energy, okay, the energy which is stored in this spark as compared to energy stored in this water, right? So this would be as follows. The energy stored in water particles combined would be greater than energy of this basically spark, right? So temperature can be greater of the spark, but the water has a lot of many particles over here, which basically have possess kinetic energy individually, right? So if I combine the total energy of the particles in the water, they will compute to a greater value compared to the energy of the particles or the electrons in the spark. Okay? So the which kinetic energy of the particle is lower in the spark? Okay? But there are many more water particles. Okay? So their total energy is greater. Therefore, more thermal energy can be supplied by water than by spark. Right? So this is very important. This is very important here, right? This point. So don't just correlate कि temperature अगर ज़्यादा होगा तो उसका thermal energy ज़्यादा होगी हमारे पास. ठीक है? And the last point which we have just seen in the last slide, the temperature is transferred from a high temperature to a low temperature body, right? And yeah, this is just a summary here. Yeah. So again, when the average kinetic energy of the particles is the same in both bodies, they are the same temperature here, right? Let's say we have water, we have boiling water here. Let's say the kinetic energy of this particular water at a certain temperature is coming out to be, let's say 5,000 joules, right? Then let's say we have paraffin, right? Paraffin also liquid. Let me draw paraffin with green. So paraffin is basically another form of liquid, right? And let's say this is also that has kinetic energy, combined kinetic energy of 5,000 joules. So if the thermal energy is same, okay, kinetic energy is same, okay, so we can say that they are at the same temperature, right? So the T2 and the T1 would be same, right? T1 equals to T2, right? So this is just telling कि हमारे पास Let's say if there was a temperature difference here, right? Let me just tell you guys over here. Let me just insert the slide. Let's say you have two containers here. Okay, let's say this is coffee. Let me just give you more simple example. You have coffee here, right? And let me draw coffee. Okay, we have cappuccino, let's say. I'm using some my drawing skills. Don't mind my skills, right? I was a student of Picasso. Perfect drawing, right? So let's say the temperature of the room is 30 degrees Celsius, right? And the temperature of the coffee is, when you bought the coffee, let's say it was, suppose it was around 70 degrees Celsius, right? When you leave the coffee in the room, what happens? Okay, the energy is basically transferred from the coffee to the room, right? Why? Because energy travels from region of high temperature to region of low temperature, right? So eventually, after some time, the temperature of coffee would basically becomes equal to temperature of room. That is going to be 30 degrees Celsius, right? So that would basically also translate that the kinetic energy of the coffee, the average kinetic energy of the particles, of all the particles combined together of the coffee, let's say comes out to be 500 joules. So that would also basically dictate that the average kinetic energy of the particles are surrounding this coffee in the room would also be 500 joules, right? I hope this example simplifies things over here. Okay, this is just stating over here. So if there is the temperature, if the temperature is same, there is no energy transfer. That also dictates that the average kinetic energy of the particles in both the surroundings would be, on both the bodies would be basically same. Okay, if this part is clear, give me a thumbs up. If this part is clear, give me a thumbs up. It's clear to Mama, it's clear to Varda, it's clear to Mashal. What about Hamza and Maeve? Clear to Maeve. That's good. Hamza, ठीक है. Hamza was finding the light button. Okay. Okay. So now we know thermal energy and temperature. How does it relate? Okay. Now let's start about specific heat capacity, right? Specific means what in physics? Can anyone tell me what does specific means in physics? You know what is heat, right? Heat is just thermal energy, right? What does specific means? This term means in physics. Or let's say general, whatever pops in your head. What should specific mean? Yes. Anyone? What do I mean by specific? Yes. Oh, Mama. Can you guess?
Sir, like specific means used to describe a quantity that's been normalized by dividing it by another quantity.
That's good. That's good. You are referring to normalization. Okay, that means कि you're studying industrial mathematics. ठीक है, जबरदस्त. A certain quantity, Mashal says. Yes. So specific basically means in this sort of chapter, you're basically going to fix mass to 1 kg, right? Or refer to it as unit mass, right? Unit means one. Okay. So that is basically going to be dealing with heat, which is going to be linking to a certain 1 kilogram mass of anything, right? Okay. So now let's start. If you know, okay, now what is specific, right? So if 1 kg of water or 1 kg of paraffin are heated in turn for the same time by the same heater, temperature rise of the paraffin is about twice of the water, right? Okay. So first of all, what is specific heat capacity? Let me just write down the definition for that. Specific heat capacity. Okay, so this is basically as follows. It is the amount of energy. It is the amount of energy. Amount of energy required to increase the temperature of a unit mass. Mass can be of anything, can be of alcohol, liquid, paraffin, anything. Unit mass by 1 degree Celsius. Okay? So how do I basically represent it? It is represented by small c. Okay? And this basically refers to specific heat capacity, right? So if I basically translate this definition to a formula, the formula becomes as follows. Okay, that C is basically the amount of energy that is required per unit mass and certain temperature, right? This is basically the formula for specific heat capacity. If I want to find its SI unit, the SI unit will be as follows. Okay. So since we have seen the formula for specific heat capacity, formula is C equals to delta E upon M delta theta. Okay. So since energy is measured in joules, mass is measured in kilograms, and temperature is measured in degrees Celsius. So therefore, the SI unit for specific heat capacity is joule per kilogram per degree Celsius. Okay. So this is basically the SI unit formula over here. This symbol means it is a mathematical notation. It means shown, right? This is specific heat capacity here, right? Acha ji. So now since we know, acha, it is, if it is clear, give me a thumbs up. This definition of specific heat capacity. Clear to Mamas, clear to Vardha. What about others? Clear to Hamza, Mashal and Mir are left. Any questions, guys? Mashal and Mir, is it clear? Hello, anyone home? Is anyone here? Clear to Mashal. Okay. Maeve, I guess, chilling out. Achha, now we know the definition, we know the relation. Let's basically quickly see what is the slide trying to say. Since the heater transfers equal amounts of thermal energy to each liquid, it seems that different substances require different amounts of energy to cause the temperature rise in the same mass, let's say 1 degree Celsius in 1 kilogram, right? So it is just saying that if we had different substances, so the amount of energy can be different to increase the temperature by 1 degree Celsius of 1 kilogram mass. Okay. So this C can vary depending upon different quantity, right? So the C for the capacity, specific capacity for water is basically 40 to 100, 40 to 100 joule per kg per degree Celsius, right? So this basically varies. So for paraffin, it is basically half. It is 2100, right? So the amount of energy required to raise the temperature of a particular substance by 1 degree Celsius by specific heat capacity. Okay? So this is basically called specific heat capacity. It has a symbol C. This is the formula which we just seen. Okay? And in terms of just words, you can define the formula as follows. That specific heat capacity equals to change in energy upon mass into change in temperature, right? Acha, so what does this symbol represents towards? Let's write those. So basically, delta E is your change in energy, right? Or the energy required, right? And M is mass. This is measured in joules. M is mass. This is measured in kilograms. And C is your specific heat capacity. Specific heat capacity. This is measured in joule per kg per degree Celsius. And delta theta is your change in temperature. Change in temperature. And this is measured in degree Celsius, right? So this is basically what is represented here. And this is, if you basically manipulate the formula, so the formula was C equals to delta E upon M into delta theta. If you take all of these terms on the left hand side, so the formula becomes delta E equals to basically MC delta theta, right? So this is basically the formula for finding change in energy using if we are given specific heat capacities. Okay. So specific heat capacity, the key definition of 1 mark is the energy required per unit mass per unit degree, per unit basically temperature increase. Okay. So if you can write this definition, this is also correct. And if you use this is also fine, right? Now you know all of the formulas. Now I want you guys to solve one question and then we can basically end the lecture. So you have guys have 3 minutes to solve the question here. Okay, Ji. So let's start solving the question. The rest can basically confirm of in between afterwards. So first of all, whenever you're given a question, always write down ki what is given to you, right? Given in sense ki what is the data given to you in hand, right? So first of all, what do you have? You have two, basically it's just saying if 20,000 joule is applied to a mass of 5 kilograms, its temperature rises from 15 degrees Celsius to 25 degrees Celsius. You want to find out the specific heat capacity of the mass, right? It can be any liquid, it can be any solid, so on and so forth, right? So you're given basically delta E here, that is 20,000 joules. You're given the mass, that is 5 kilogram. And what else you're given? You're given the T1, that is 15 degrees Celsius, and you're given T2, that is 25 degrees Celsius. So you want to basically find what? You want to find two things here. You want to find delta T first. What is the delta T? And then you want to find basically the required thing, which is basically specific heat capacity. Okay. So now let me insert a blank slide, not this one, a blank slide. So let's first of all find delta T. How do I find delta T? It is just the change in temperature, that is T2 minus T1, right? That is 25 minus 15. That gives you a delta T of 10 degrees Celsius, right? Then you want to find basically the specific heat capacity. What is the formula that relates all of the things? That is E equals to mc delta theta, right? This symbol means theta. It's a Greek symbol. Okay, just put in the values. It was 20,000 equals to 5 into 10 into, sorry, C is unknown. That is C, right? So C is going to be equals to 20,000 divided by 50. This 0 cancels out. So 5 ones are 5 4 is 20. So it's 400, right? The C value is coming out to be 400 joule per kilogram per degree Celsius, right? If your answers matches with my answer, kindly give me a raise of hand. Now let's talk about the importance of high specific heat capacity of water, right? So this is basically specifically focusing on high specific heat capacity of water. Can anyone tell me what is the value of specific heat capacity of water? We did this in the last class. Can anyone guess? It was what? It was 4,200 joule per kilogram per degree Celsius, right? And specific heat capacity of this is of water. And specific heat capacity of basically sand is 800 joules per kilogram per degree Celsius, right? So can anyone compare by just seeing the specific values? Okay. First of all, what is specific heat capacity? It is the energy required. Let me just. What is basically C? It is energy required to increase a mass, to increase the temperature of 1 kilogram mass by 1 degree Celsius, right? That is basically called specific heat capacity, right? Now comparing these values, that the capacity, the specific heat capacity of water is 4,200 joule per kg per degree Celsius, and the specific heat capacity of sand or soil, okay, is only 800 joules per kg per degree Celsius. Now imagine this and note these values and compare these things, right? So you have C that contains water, obviously, yes. And then you have the land, right, which basically contains sand. It is near the sea, which is sand, right? So can anyone now compare these values? What is the importance of this? What thing will get heated up first? First, the fast rate, sand or water? Hmm. If we basically use the values of capacity, specific heat capacities of sand and water that is mentioned at the top right. Just imagine a seaside, right, where you have sand and water. Just looking at the sea and looking at the sea definition on your top left, which thing should get heated up fast, sand or water? Anyone guess it? So give me a guesses. So those who think sand would get heated up faster as compared to water, raise your hands. Okay, other things कि sir sand will get heated up faster as compared to water. Hamza to Mem also. Maeve thinks ke water will get heated up faster. Okay, so the majority wins over here. That is correct, right? So what is this particular value saying? The specific heat capacity of 4200 means that for increasing 1 kilograms of sand by a temperature of 1 degree Celsius, you would need 4200 joules to basically just cause it. However, if you basically compare the specific heat capacity of sand, it just needs 800 joules. Okay, if you have 1 kilogram of sand and if you want to increase the temperature of 1 kg of sand, you would only need 800 joules of energy, right? So that is why, if you notice, if you go to seaside or sea view or any, let's say, uh, ocean side, so you would feel in the morning that the sand is hotter as compared to the water, right? Okay. So it takes it takes time and a huge amount of energy for the water to completely warm up as compared to sand. Now let's imagine that it is the night time, right? It is the night time now. Now you have clouds because all dark. It's the night time. So you have clouds. So which would get cooler at a faster rate? Sand or water? Now let's say in the daytime, sand got heated up pretty faster at a faster rate, but water heated up slowly. Okay, because it wants more energy to basically increase the overall temperature of the water or the ocean or the sea. Now compare that the sun has set it and it is in the night time. Which part, sand or water, would cool down at a fast rate? If you guys think it is sand which is going to cool down at a faster as compared to water, raise your hands. Okay, Mama thinks that sand would cool down at a faster rate. Okay, Vardha also thinks that. What about the rest? Okay, so yeah, just imagine that it basic sand needs to basically lose less amount of energy to basically cause a drop of 1 degree Celsius, right? But this basically needs to lose 4200 joules. That means it has to lose more energy at night to basically cause a drop of it by 1 degree Celsius, right? So this is the importance of high specific heat capacity, and that is the reason water is used in car as lubricants. Have you ever tested your car's engine? You put some water in your car engine when basically it causes it to cool down. Have you seen that? If we have seen, yeah, Vardha has seen that you put some water in your car engine to basically act as a coolant. Okay, so it is a cheap lubricant which is basically used to cause cooling effects also. Okay, because it gets slowly heated up. Okay, so it can absorb more amount of energy from the engine as compared to other lubricants. Okay. So let's hear it out. Let's see what is mentioned in the slides. So that basically summarizes what we have discussed right now. The specific capacity of water is 4200 joule per kilogram per degree Celsius. Of soil, of sand is basically 800 joules. As a result, the temperature of sea rises and falls more slowly than compared to land, right? A certain mass of water needs 5 times more thermal energy than the same mass of soil to rise the temperature by 1 degree Celsius. Because what is 4200 upon 800? What is the ratio of sea capacity, specific capacity of water and specific heat capacity of soil, that is 4200 upon 800, right? That is around roughly around 5, right? 5 times. 8 5 is the 40. Okay. So water has also basically give out more energy to cause a temperature drop of 1 degree Celsius, as we have discussed. It has stored 4200 joules of energy in 1 kilogram of mass. Okay. So basically, if it has to lose 4200 joules of energy into the environment, it will take more time, right? That is why it falls slowly. Some islands are surrounded by water. They experience much smaller changes of temperature from summer to winter. Okay, then large land masses such as Central Asia, right? Have you seen कि Karachi temperature does not basically goes to extreme? Who lives in Karachi, by the way? Can you raise your hands? Those who live in Karachi, raise your hand. Okay, Varda lives in Karachi. Hamza lives in Karachi. Okay, so in right now we have basically winter, right? And the temperature is dropping to around 9 degrees Celsius. Okay, it was the minimum in the winter, right? But if you talk about Murray or northern areas, it goes to -5, -10, right? So in summers, we also have a maximum of 31, around 35. Okay? But at extremes, sometimes at heat strokes, we have 45 also, right? But the temperature does not vary that much, right? So it is between 35 to 9, right? If you talk about Antarctica, it basically goes to -20, -30 degrees Celsius in the night. And in morning, it can basically goes to around 12, 15 degrees Celsius, right? So that's a huge variation over here, right? So that is the benefit of having sea at around near basically near your region or your country or your city, right? So the high specific heat capacity of water basically, and as well as it is cheaper, right? It is freely available from the oceans. Okay. And 75% of Earth is made up of water, right? 75% of Earth is water. So that basically leads to the more availability of water throughout the entire world. Okay. So it is used in cooling engines, okay, and radiators of central heating system, right? In the cars and in your, let's say, the water heaters in homes, right? Okay, so this is the importance of high specific heat capacity. So now you should know, okay, what does it mean, right? Instead of just learning the formula and just knowing, okay, how do we solve it, we should know what does it mean, right? If it is clear, give me a thumbs up. Can we solve a question together? If till here it is clear, give me a thumbs up. It's clear to Mama. It's clear to Varda. What about Maeve? Clear to Maeve. Hamza, are you here? It's clear to me, Hamza also. Okay. Now, since you have you have caught the importance of heat specific heat capacity of water. So let's solve a question. I will give you guys 4 minutes, and you should already know, okay, how do we find power, right? Power is energy upon time, and the formula for energy using specific capacity of this. Okay, so we have to use these two formulas here. You guys have 4 minutes to solve it out. Okay, so I guess everyone is done. That's good. So let's start solving it out. Let's see if your answers are correct. Okay. So over here, what do we have? Let me just first of all read the question. A tank holding 60 kilogram of water is heated by a 3 kilowatt heater, right? The specific capacity of water is this. Estimate the time, the temperature. That we want to find the time it takes for the temperature of the water to rise from 10 degrees Celsius to 60 degrees Celsius over here, right? So what is happening over here? We have a bucket of water. You have a bucket of water, and you basically are heating it up. Okay, from you are heating it from a immersion heater, which basically contains coils, and it is basically giving you a power of 3 kilowatt. And you want to basically increase the temperature of the water from 10 degrees Celsius to 60 degrees Celsius. ठीक है? So this is a scenario which is given to you. First of all, whenever you start a question, always write down the data that is given to you. Okay? So what is given to you? You have the mass of the water that is being heated up, that is 60 kg. You have what else? You have the power of the power rating of the heater, that is 3 kilowatt. And you should know what does kilo means. Kilo means 1000, right? 10 to the power 3. And you have specific heat capacity of water, that is 4200 joule per kg per degree Celsius. And you want to basically find delta T, delta theta, that is going to be 60 minus 10, and you want to increase the temperature by 50 degrees Celsius. So what you have to find out? You have to find out basically the time it takes. Okay. The first step should be basically you should be able to find out the amount of energy you need to provide to water, right? To cause the temperature increase from 10 degrees Celsius to 60 degrees Celsius over here. So you want to find first of all delta E. So delta E can be found out using MC delta theta. Okay, and delta E is basically just put in the values here. So mass is 60, your C is 4200, and your delta theta, that is the changing temperature which you want, is 50. Okay, so your delta E therefore should be coming out to be, let me calculate the answer. So it should be in joules. So it's coming out to be 60 into 60. Okay, what is happening here? 60 into 4200 into 50. So it's coming out to be 12.6 megajoules. 12.6 exponent 6 joules, right? So, and now you want to find time, right? And how do you relate power, energy, and time? So power is change in rate of change of energy, right? So from here you can make T subject. That is going to give you the T equals to delta E over power. And now you have everything, just put in the values. So it's 12.6 exponent 6. And the power is given to you as 3 kilowatt, right? 3 kilo means 1000. So it's 3000 watts. So it's going to be 3 exponent 3. Now just solve it out. 3 exponent 3. And you're getting basically 4200 seconds. Right? That is the answer. So it will take 4200 seconds. And if you want to find the time in minutes, let's do that also. So you have that T in seconds, that is 4200. If you want to get it in minutes, you can divide by 60, right? So the time will come out to be 70 minutes. If you want to find this in hours, you can further divide by the 60. Okay, and that is going to be come out to be 1.17 hour. Right? So that is the amount of time it will take for the entire 60 kg of water in the container or in the tank or in the bucket to basically increase its temperature from 10 to 60 degrees Celsius. If your answer is matching, give me a thumbs up. Okay, Vardha's answer is matching. Everyone's answer is matching except Hamza. Okay, that's good. Everyone got the same answer. TKG, that's good. So now we should move on to the part B. Yes, now you have again 4 minutes. So these are important questions, right? So majority of the theory questions will be using these formulas in your paper 2. You have 3 minutes to solve the question. And then if you're done, you can raise your hand. Okay, Maeve is done. That's good. Maeve, are you sure you're done? Okay. I guess you're bluffing. Okay, Ji guys, I believe that most of you are done. So let's continue. So Mashal, we are doing some questions here. So we can watch the remaining part in the recording, okay? Okay, Ji. So let's start solving this question. So what do you have here? You have a mass of aluminum that is of 0.5 kg. So let me just draw a mass of aluminum, right? Let's say this is the mass of aluminum. This is the mass of aluminum, and it has a mass of 0.5 kg. It is heated from 100 degrees Celsius. It is heated 200 degrees Celsius, right? So that is the final temperature, T2. And then it is placed in 0.4 kilogram of water at 10 degrees Celsius, right? If the resulting temperature of the mixture is 30 degrees Celsius, what is the specific heat capacity of aluminum if the specific heat capacity of water is this, right? Okay, so what is happening here? Because you have the case A, you have to think. It's not difficult, it's just you have to make sense of it. कि हो क्या रहा है. So the first scenario is this: you have an aluminum that is at temperature 100 degrees Celsius, right? Let me just erase this, and it has a mass of 0.5 kg, right? Then you have basically case 2, that is, okay, you're putting this aluminum rod into the bucket of water, right? And let me just basically make this. Let me make this. So you have now this scenario over here, right? Okay. So you have this basically the final temperature of the mixture. Mixture is basically the aluminum rod is in the liquid, right? So the final temperature of this mixture is basically T2. You can say here is 30 degrees Celsius over here, right? And prior to this, we had one more condition that the water was basically initially at a temperature of 10 degrees Celsius, right? The initial temperature of water was 10 degrees Celsius. Okay? And one more thing which I missed was, okay, the mass of water, which is basically mentioned here, is 0.4 kg. ठीक है जी. So अब you want to basically find out the specific heat capacity of aluminum rod here. So what was your approach? Can anyone basically wants to share his or her approach? So यहाँ पे सिनेरियो ये है, ये एग्जाम में आपके एग्जैक्ट क्वेश्चन आता है पेपर 2 के अंदर, एंड बच्चे इसमें कंफ्यूज हो जाते हैं. So इसमें you would have to basically see some things over here, right? So you have basically, I'm going to draw block diagram here, right? So over here you have water at 10 degrees Celsius, right? Then here you have basically the aluminum rod at 100 degrees Celsius, right? Then they're combined together. ठीक है, the mixture is basically finally kept at 30 degrees Celsius here, right? So does this block diagram make sense to you guys? If yes, give me a thumbs up. Okay, it makes sense to everyone. Okay, so now what should we do? Can anyone share the next step? What should be the next step now?
Sir, we should minus the water at room temperature and at 100 degrees, and then multiply that by the mixture at 30 degrees, and then divide that by 4200 joules.
Okay. Yeah, that's good. Basically, now you have to basically use law of conservation of energy, right? So this is basically if you mix two things, right? This was basically water. Okay, it was at 10 degrees Celsius. Then you have aluminum rod, right? This was at 100 degrees Celsius. You're basically mixing them together over here. So something is going to basically absorb the energy and something is going to basically release the energy over here. So what does the law of conservation of energy says? What is the law of conservation of energy? That neither energy can be destroyed nor created, but it can change from one form to another form over here, right? So यहाँ पे we will have to mention a equation over here, and that equation will be what? That energy lost by water, sorry, by rod equals to energy gained by the water, right? The final temperature of both of them is going to be 30 degrees Celsius over here, right? So you have T1 for the rod, and then T2 is basically for the rod is this. And then you have T1 for the water, that is this. And then T2 again remains same for the water, that since it is combined together, that is called a mixture, right? So now we can write the equation over here as that energy of water equals to energy of rod, right? And the formula is M of mass of water. Take, I'm using W for water. I'm using small r for rod, right? Mass of water times specific heat capacity of water times delta theta equals to mass of rod times specific heat capacity of rod times delta theta. ठीक है? Okay, now from seeing this block diagram, what is the delta theta of water here? And what is the delta theta of the rod here? Yes, anyone? What is the change in temperature required for water? You only want the difference, right? You don't want the signed value over here, right? So for water is basically going to be 30 minus 10, right? That is going to be 20 degrees Celsius. ठीक है? And for rod, it's going to be 100 minus 30, that is 70 degrees Celsius. Does this part make sense? If yes, thumbs up. How do you got the delta theta over here? Okay, makes sense to everyone. Hopefully, yes. Now just put in the values and get your answer. Okay, so this was such an interesting question over here, right? Mass of water is given to you as 0.4 kg, right? Sorry. So it's 0.4 times specific capacity of water. That is 4200. And what is the changing temperature required for the water? That is 20 degrees Celsius. Here, right? And then what is the mass of rod given to you? It is 0.5. And the specific capacity of rod is unknown. But you know the delta theta of the temperature change in rod, right? That is the 70 degrees Celsius, right? From 100 to 30, it's got drop over. Just want the change. We don't want the signed difference, right? It's going to be 70 over here. So we just make the specific capacity of rod subject. And what is it coming out to be? So it's 0.4 into 4200 into 20. That is 33600 divided by 0.5 into 70. So it's coming out to be 960. The specific heat capacity of the aluminum rod is coming out to be 960 joule per kg per degree Celsius. If anyone's answer is matching, raise your hand. Anyone's answer is matching, raise your hand. Okay, so I believe you have learned a new thing here, right? Okay, how do you find this particular scenario's answers? If it is clear to you, how do you solve it? Give me a thumbs up, then we can move on. Okay, it's clear to Hamza, clear to Varda, clear to Mama and me. Mashal, is it clear? It's just an application. This is the formula which you learned in the last class. It is just getting applied to different scenarios. Okay. Mashal can watch. Okay, I have a comment here. Got it. Okay, that's good. So now gonna basically start some procedures, some methods, right? Some change of states. So we have briefly discussed this in the start. Okay, what is melting, boiling, and evaporation वगैरह. But now I'm going to basically learn the cooling curves, heating curves, some new formula that is called latent heat of fusion and latent heat of vaporization. ठीक है. And we're going to basically talk about this till here. ठीक है. Solidifying, melting and boiling. We start from latent heat of fusion in the next class inshallah. So before starting, I want someone to explain melting, boiling, and evaporation, right? Explain these terms. What change of state occurs in melting, boiling, and evaporation? Yes, I want someone to participate. Please, it's a simple question. Yes, anyone? If not, I will choose someone. Okay, let me choose someone. And it's going to be Varda. Varda, can you explain melting, boiling, and evaporation? What basically happens in this? Whatever you know.
Okay. Sir, melting is when
Mm-hmm.
temperature. Sir, I mean, it gains temperature and then its state changes from solid to liquid. Boiling is when you heat up a liquid and it gains temperature or energy, then it evaporates. No, it starts to boil without. And evaporation is when a liquid. एक second, sir.
Mm-hmm. Think a word. Yes, give me a guess. No worries.
Basically, evaporation is when the state of liquid changes from liquid to gas and it gains energy.
Hmm. That's good, right? That's good. So basically, melting, boiling, and evaporation are just basically change of states. ठीक है? So before starting this, let me mention the changes of state here. कितनी होती हैं? The changes of state. What changes? Change of states. We have as follows. We have melting. We have boiling. We have evaporation. I believe we have done boiling evaporation in the last chapter. If you recall it, give me a thumbs up. We have done the differences also. What are the differences between boiling and evaporation? Have we done this or have I done this with another group? Can you guys recall it? We have done boiling and evaporation and the changes of state in the last chapter. Can I take part in the motor matter? Do you guys recall it? Then we have yeah, no sir, I don't think. Okay, I guess मैंने किसी और को कराया, दूसरे ग्रुप को कराया हम लोगों ने. ठीक है, so some groups are going आगे पीछे. तो yeah. So we have melting, boiling, and then if you go back, we have condensation. ठीक है, then we have freezing. ठीक है, and then we have basically okay. So this basically melting is solid to liquid, and this is boiling is basically liquid to gas. And evaporation is same liquid to gas, but boiling and evaporation has some differences, which you will see in a while, right? And those differences come in your exams. Condensation is basically what? It is gas to liquid, and freezing is basically liquid to solid, right? So we have one process missing over here. Can you identify that? We have one change of state missing here. That basically converts Solid to gas. Which process is that? Yes.
Sublimation.
Yeah, that's good. We have sublimation. Okay, so these are the change of states which we will study over the end of the chapter. So we have almost completed the chapter. So these part is remaining, which basically includes latent heat of vaporization and fusion. That's it, right? Then we'll solve some questions. Then you'll have two tests followed. Okay. First of all, pressure. So you haven't been tested on pressure, and then you will have a test on thermal properties and temperature, right? So recordings मैंने upload की थी, but वो I don't know how. I guess the uploading में के अंदर it was an error. So I will try to upload them again, ठीक है? After my classes, inshallah. So don't be worried about that. So these are the processes over here, right? So let's discuss these processes in detail and let's see what are these, ठीक है? So यहाँ पे this is basically part of heating curve. ठीक है? We'll see in a while ये होते क्या हैं, what are heating curves. Just now know कि heating curves के part हैं processes. ठीक है? And these basically part, not this, these two specifically are basically part for cooling curve. This is one of our exception over here, right? Exception which we have in the processor, which basically directly converts from solid to gas, right? So this we'll study this in a while, right? So first of all, starting from melting, okay? What is melting? Let's see what is melting. We have procedure number A, that is melting. So melting is a change of state. It is a change of state from solid to liquid, right? And specifically in this, we have a point, right? A point when the solid starts to convert to liquid. It's basically called the melting point, right? Melting point, right? So now let's start to sketch the heating curve. Right? This is x-axis is showing time in seconds, and the y-axis shows the temperature in degrees Celsius, right? So what happens initially? The ice is basically at 0 degrees Celsius over here, right? So the curve starts from the origin, right? So it goes like this. Okay, there is a point here. Okay, so you can see here during this particular trend, this particular blue trend, what is happening here? This is basically it is liquid. It is basically solid liquid here. It is solid and liquid both here, right? Because the change of state is basically starting to occur over here, right? And this particular point, let me call it A, is called the melting point, right? And then after this particular point, the temperature becomes almost horizontal. Okay, the graph becomes constant. There is no change in the temperature over here, right? So this is the initial part of the heating curve, right? This is the initial part of the heating curve here. Okay. Now, what is going to happen here? So now we have learned these things here. So now let's move on and let's see what is boiling and evaporation, right? Okay, this is something else. This is a cooling curve. Okay, let me insert the blank slide here. Now we have cooling. So it is the process in which basically there is a change of state. There is a change of state from liquid to gas. Liquid to gas, right? And the point at which the liquid starts to convert to gas is called the boiling point, right? It's called the boiling point. Now let's sketch the complete graph, the complete heating curve. This is time in seconds. This is temperature in degrees Celsius. Now let's sketch the graph. Right? So we should not need the rest. This is solid liquid and then gas. Yeah. So we have point A, we have point B, right? And then over here we have 0 degrees Celsius, we have pure ice here, right? So before we have seen that point A is the melting point. Right? So over here, what is happening here? So now what do you see in the graph? Okay, let me fix one thing here. Okay, so this basically point A is going to be here. So you have point A, point B here. ठीक है जी? Okay. Now let's move on ताकि मैं mark कर दूं point C से. This is going to be A, B, C. Yes. Now can you explain कि हो क्या रहा है यहाँ पे? So क्या हो रहा है यहाँ पे?
Sir, it's showing how the temperature increases, so the energy also increases.
Hmm.
And then when from B to C, it's a straight line, so the temperature is constant until it goes like from C and above.
Yes. Now, so can you tell me कि यहाँ पे which one is the boiling point? Is it A, B, C, or D?
Sir, B.
Okay. So यहाँ पे basically क्या हो रहा था हमारे पास? So in this part we have solid, liquid combined together, right? And then we have pure liquid here, right? And then in this part we have liquid and gas combined in a single way, single graph. And then over here we have all of them to be gas, right? So at what point liquid starts to convert to gas, which is the point where you basically see the liquid is starting to convert into gas. Yes, that is basically this, right? After if it crosses point C, you can see the liquid is starting to convert some into gas, right? So you have liquid and gas combined. So at point D, it is completely the entire liquid is completely in gaseous form, right? And if I talk about water over here, we talk about water, the boiling point of water is 100 degrees Celsius, right? And you can see that this particular point D would be at 100 degrees Celsius, right? So this is basically the region where it has basically completely converted to gas. Make sense? If it makes sense, give me a thumbs up. If it makes sense about the heating curve, give me a thumbs up, guys. Yes, it makes sense to Varda only. What about the rest? Yes. Okay. ठीक है जी. If you want me to explain it again, I can do that. If someone wants me to explain this again, give me a thumbs up. Yes. किसी को अगर एक्सप्लेनेशन वापस चाहिए तो मुझे बताएं वापस आप. अच्छा, let me fix one thing ताकि it makes sense to you guys in a better way. ठीक है? So let me just try to fix one thing here. ठीक है? Let me make it again clearly ताकि it makes sense to you guys. This is very important. This comes in MCQs theory सब में. Don't just basically skim it out. Okay. So let me just, yeah. So we have this graph here, right? This is time in seconds. I'm going to draw 0 degree Celsius here, right? 0 degree Celsius point here. This is the zero value, okay? This is, let's say, negative 10 degrees Celsius, right? And this x is in degree Celsius over here. This graph basically starts here. It goes like this, and then this goes like this. Okay. So over here we have how many points? We have again point A, we have point B, right? So in this particular state, in this particular section of graph, everything is in solid form, right? And in this particular state of graph, the basically solid and liquid starts to exist together because change of state is happening here. This particular point A is called the melting point, right? Because this is the point at which the melting process is starting. Is this point clear? यहाँ तक clear है? If yes, thumbs up. जल्दी से. Okay, clear to everyone. Varda and me. ठीक है. So now this is just a point. It makes sense also कि यहाँ पे it starts to melt. Everything below zero should be basically ice, right? And at zero, it basically causes a horizontal line. So this is basically where some new energy will be will basically acting as a role to convert the change of state, which we will see in a while. Now I'm gonna combine it together, ठीक है, into this. So इसको मैं बना रहा हूँ into another section of graph. Let me make it on another point. Let me just make it bigger and better. Okay, empty new slide. Now we have the new graph, which is as follows. This is time in seconds. Okay. This is negative 10 degree point, right? And this is the zero crossing. This is the zero axis value over here. Here we have 0 degree Celsius, right? And this is theta n degree Celsius. Before we have studied here, we had this trend, it was constant, and it goes up, and then it goes like this over here, right? Then it goes here, right? Okay, so let me just make it smaller. ताकि ये बाहर ना निकले screen से. So you have these crossings here, right? Let me make it properly ताकि you have a better idea. And this particular point is the 100 degree Celsius point, right? So you have point A, you have point B, you have point C, you have point D, right? So this is point A, point B, point C, point D, right? Over here, since it makes sense, before zero, below zero, everything should be solid. It should be ice. So this is solid. In this region, we have solid and liquid combined together. And in this region, we have everything in liquid form, right? And then in this particular section, we have the state between liquid and gas combined together. And then here in this section, we have everything in gaseous form, right? So we have some important points here, which is point A. Then we have point B. Then we have point C, sorry. Okay. So what is point A, by the way? Point A is the melting point, right? Because you can see it was solid before. After crossing this point, the states basically are existing between solid and liquid combined together. So melting start over here. Okay. And then we have point C. You can see at point C, we have the boiling point, and it makes sense because it is at 100 degrees Celsius. Okay, boiling starts at 100 degrees Celsius over here, right? And you can see at this particular stage, okay, you have this state that is in liquid and gas combined together. Before it was only liquid, right? यहाँ पे boiling start over here. And after you cross D, you have everything in gaseous form. Okay, so this is basically the heating curve over here. If it makes sense, give me a thumbs up. Okay, makes sense to Mama, makes sense to Varda, makes sense to Mashal and Hamza. That's good. I believe in ours clear. If you know this, the cooling curve shall be the opposite, right? So now I want you guys to label this. Okay, so this is your homework from before the next class. Part A is basically label. Okay, the condensation and freezing point. Okay, and part B is label the states at the marked regions. Right, let me mark this as A bar. This is B bar. Right, so what is going to happen here? So similarly, you are asked to label for the cooling graph, and if you basically are, if you have submitted all of your homework, so let me just discuss the answer, that we can proceed again. Okay. So condensation, basically you are having condensation over here. Okay, then you're having basically freezing over here. So what is condensation, by the way? What is condensation? Mama, what is condensation?
Sir, when gas hits a cold surface, it slowly and gradually turns into liquid.
So it is a change of state when the gas starts to convert into liquid, right? So you can see it's a
Again.
cooling graph, and from initially at A bar, the point A bar is the point at which you have only gas, right? So now we're basically decreasing temperature. So then you hit point A, and then you have point B, and then you have point B bar, right? Can you explain the trend over here? What is happening? Let's say if you have a gas, how is this representing the cooling graph? What is this showing over here? If you have done your homework, you just explain your answer.
It shows that it goes from gas to liquid. It cools down at
Mm-hmm.
point A. It starts down gas to liquid, and then from A to B, it stays that way. Like it starts cooling down, and then from B.
That's good. Perfect, right? You can see that uh, this is the point when the basically gas starts to convert into, sorry, the gas starts to convert into liquid, right? So this is called the condensation point here, right? This is called the condensation point. Okay, over here you had gas state, and then from A to B you have gas and liquid at the same time. This is the point where basically the state of change is occurring over here. Then at point B bar you have the freezing point, right? So over here, what is happening? It is basically gas. It is basically not gas. It is liquid here. And then after B bar, the state basically change start to occur. And then here you have liquid and solid at the same time. And at point B double bar, you would have only solid state, right? So that is how state of change is occurring here, right? So these are the points which you had to basically mark and label and explain. Okay. अच्छा जी. Now this the important point which I want to highlight in this graph is region is basically region AB and region CD over here. ठीक है. As you can observe over here, the actual change of state is occurring between AB. ठीक है. So over here we have a phenomenon that is called latent heat, right? So that is very important here. So latent heat sort of an energy which basically constitutes to a change of state at constant temperature. You can see that temperature is constant here, right? The temperature is constant, it's not varying. ठीक है. So this basically is called latent heat of. So what types of latent heat do we have? We have basically two types of latent heat. We have latent heat of fusion and latent heat of vaporization. Okay, so this section is called latent heat of fusion over here. Okay, so we will see it in a while. क्या होता क्या है? Just try to basically just mark out the points. Okay, we want to discuss these points, right? Over here, the change of state is basically actually occurring at a constant temperature of 100 degrees Celsius. So over here we have latent heat of vaporization. ठीक है. So before starting the discussion, I want to ask from you guys, okay, what do you think? What is latent heat? If you have any memory of the latent heat definition or whatever you want to basically guess, I want a feedback from you guys so that we can plan the lecture accordingly. So, Mema, what do you think? What is latent heat?
As you said, I think it's like the heat changing of state, I guess, which is like staying constant, as you have pointed out in the graph,
Mm-hmm.
like solid to liquid.
Mm-hmm. That's good. What about Varda? Varda, what do you think? What is latent heat?
Me, sir.
Yes.
I think latent heat is like maybe the heat that's like um that's not used in excess, I guess.
Mm-hmm. Not in excess? So what is it? What does it do? Bus explain that.
And it's like sir, it's just वो होती है एक ऑब्जेक्ट के अंदर
See.
latent heat.
Okay. So what about Mashal? Mashal, can you comment on this in chat if you want to? Okay. So I just want to have so Umema says here it's the heat required that basically does the change of state at constant temperature. Okay, that is pretty close enough. Further says here it is the hidden energy that is basically causing the actual change. Okay, that can also be acceptable. We also have other members here. Hamza, what do you think? What is latent heat, by the way? Yes, Hamza.
क्वेश्चन रिपीट कर दें.
What is latent heat?
What is reactant heat?
Latent heat, latent.
So the heat required to break the bond between an object and an object.
That's good. आगे add on to it.
तो वो कांस्टेंट रहती है जब कोई प्रोसेस हो रहा होता है.
क्या
मेल्टिंग,
कांस्टेंट है?
बॉइलिंग.
क्या कांस्टेंट है?
ये हीट टेम्परेचर.
That's good. ठीक है. So yeah, that's what I wanted. So I guess every part basically person did participated and gave me some important points. So we're gonna combine all of them together in the definition, right? So let's move on. So then we have solidifying, melting, and boiling. So we have discussed basically boiling here. We have discussed melting here. So let's discuss the condensation and condensation here, right? Condensation and freezing. And then we can start and move on. Okay, so we have the other states of change of states, that is as follows. Okay, so let's start the remaining change of states, right? Then now the third one which we have in the bottle, in the sort of bucket list is basically not condensation, right? Let's start from here. We already have basically given the answer. Let's basically write it down formally. So condensation is basically the change of state, the change of state from gas to liquid, right? TKD. And then over here we have a condensation point. So what is condensation point? Let's write it down. Condensation point. It is the point at which the liquid, the gas, starts to convert into liquid. TKD. So this is very two important definitions, right? You might be asked about this in the exam. ठीक है, the definition or the condensation point, right? So you should know all of both of those. ठीक है. So next in the pipeline we have the freezing here, right? That is again very important change of state. That is called also solidification or freezing. Both are same, right? Then we have freezing. And as you have basically already mentioned, Kisa freezing is this change of state when the liquid starts to convert from to solid, right? So change of state when the liquid converts to solid, right? And again over here we have a freezing point, which you all should know. Okay, what is it? You already mentioned or labeled them in the graph, but now we are basically writing down the formal definition, right? Then we have freezing point. ठीक है, and it is as follows. The point, it is the point at which the liquid starts to convert into solid. Starts to convert into solid, right? So these are the change of states which you all should know and learn for the exams. So from these two states which we had done in the last lecture, that was melting and boiling, you can create the heating curve. And from these two states, that is condensation and freezing, you can create the cooling curve, right? And you have also labeled the points here. Okay. Similarly, you can highlight, you can signify that there are 2 points regions where some latent heat is also doing some work, right? Okay. So now keeping that in mind, let's basically quickly skim through the content which is labeled in the slide. The previous experiment showed the temperature of liquid stirring room that is solidified. Okay. The cooling curve which I have already labeled in the last homework assignment. Okay, that is 22.2.13. That is this. Okay. It shows for a pure substance the flat part AB occurs at melting temperature, right? So when the substance is basically solidifying. Okay. Due to solidification, the substance transfers thermal energy to surrounding, but its temperature does not fall. Conversely, when solid is melting, the energy supplied to does not cause a temperature change. It is just basically mentioning the parts over here. Okay, these parts, the section A, B, and B bar and B double bar, and this section AB, which will basically check over here. Okay, what energy is causing the change of state actually over here, right? Because we are having a flat region here at constant temperature, so something is happening between these regions. Okay, that is basically causing the solid to change into liquid, right? So what is that part? So they're basically sort of building a story here, right? For example, the temperature of a well-state ice water mixture at let me 100 degrees 0 degrees Celsius until the ice is melted. Okay, we're just saying that if you have the bucket of, let's say, you can do the experiment at home. Take a glass of ice. Okay, you can take a glass of ice cubes. Okay, and you can just keep stirring it until it changes to liquid, right? So until all the entire basically content of the ice is converted into liquid, you can just put a thermometer here. Okay, and keep noticing the temperature. Okay, till and before, ठीक है, everything is converted into liquid, the temperature of the thermometer will basically remain at 0 degree Celsius, ठीक है. We're just explaining this point here, ठीक है, that when the freezing part is occurring here, the temperature basically stays constant, right? If you basically talk about the heating curve, until and unless basically entire basically solid converts into liquid, the temperature in this part basically remains constant. That is at 0 degrees Celsius over here. So something is basically causing the state to change. Okay, and what is that called? We already discovered that phenomenon that is basically called latent heat. Okay, so this is sort of an energy. Okay, that is basically taking place at constant temperature, and it's basically leading to a change of state, right? So just explaining this, okay? So similarly, they are saying that when you are basically having boiling, so the temperature remains constant. Okay? You can see that from section CD, okay? When the boiling is occurring, there is a section which basically that is called CD, when the temperature is again constant. So there is again some form of energy which is taking place to change the state from liquid to gas, right? So again, what is that? That is called latent heat of vaporization. Okay, so the change of state that is causing the liquid to transfer into gas. Okay. Okay. If is it clear till now? If yes, give me a thumbs up so that I can move on. It's clear to Hamza. ठीक है. Clear to Umama, Maeve, Varda. What about Mashal? Okay, that's good. So now since you know the background of the story, okay, that what we are going to face now, okay, that what is it, right? What is the phenomena that is changing the state, right? We're surprised that the temperature is remaining constant, okay, and there should be some form of energy transfer that is causing the state to change, right? That is basically causing the solid particles to get loosened up to create space between each other such that they can move freely, and hence we have liquid state, right? So if you recall the kinetic theory of matter chapter, right? So we have learned in the kinetic model of the solid liquid, right? How are the particles arranged in liquid? They're freely to move around each other, right? Okay, so that is basically if you talk about the region AB, right? This particular region. So in this particular region, you basically are using latent heat of vaporization. Not vaporization, latent heat of fusion, sorry. Okay, so the energy which is basically causing the change of state from solid to liquid at constant temperature is called the latent heat of fusion, right? This is the energy which is causing the magic to occur, right? So let's see what is it. Let's see what is this particular energy and what does it do. So energy is that is transferred to a solid during melting or given out by a liquid during solidification is called latent heat of fusion, right? Latent means hidden, right? As Varda said, it's hidden, right? And fusion means melting, right? So latent does not call temperature change. It basically seems to disappear. Okay. So what is basically latent heat? Let me just basically dictate here. Okay. So this term represents hidden, right? And you all know what is heat, right? Heat just is just form of energy. So what is latent heat? It is the energy. It is the energy that causes the change of state at constant temperature, right? So all of your answers obviously combined together here. Someone mentioned hidden, someone mentioned constant temperature, some mentioned K. It is energy which causes the change of state. So yeah, that was good. Okay, so everyone knows some bits. Okay, at constant temperature, right? So if I want to define it formally, okay, so for specifically for state going from solid to liquid, right? Okay, so we have melting process here, right? So if you see the heating curve, this is sort of this. ठीक है, जीरो एक्सिस हमारे पास ये है. ओके, व्हाट हैव आई डन? ओके, so you have the 0 degree Celsius here. So if you start from here, you basically get this trend, right? You have point A, B. So this is the region in which we are interested right now. Okay. So this is the region where the melting is actually occurring, right? That is basically changing solid to liquid, right? Let me write it here. That is changing solid to liquid. So here we have latent heat of fusion over here, right? So what is specific latent heat of fusion? So it is basically it is shown by LF. Okay, it is the quantity of heat needed to change unit mass from solid to liquid without temperature change, right? So we have latent heat and then we have latent heat of fusion. Okay, so let me just mark it here. We have this phenomena, latent heat of fusion. So it is the energy. It is the energy required to change the state from solid to liquid at constant temperature, right? And for this, we have a formula that is called E equals to MLF, right? Where E is what? E is basically your latent heat energy, and M is your mass. It is measured in joules. M is your mass. It is measured in kilograms. And LF is basically your specific latent heat of fusion. Just if you recall the formula from the last lecture, we had E equals to MC delta theta. So E was energy, right? Energy capacity. Okay. And this was specific heat capacity, right? So similarly here, if you recall, if you basically match the dots, it's almost similar. Specific heat capacity. Energy is same as heat, right? So if you connect the dots from there, so it's almost same, right? This is specific latent heat of fusion. And it is measured in joule per kg. Okay. So now if I ask you a question, K Mashal, let's say what is LF? Okay. If you want to define LF in a definition, so how would you define it? Okay. You define it as follows. That LF is basically, if you just see the formula is E equals to MLF, right? If you make LF subject, that is the specific latent heat of fusion, that is going to be E over M, right? And if I was basically want to find out what is 1 joule of latent heat of fusion that is required, right? If you want to make it 1 latent heat of fusion, okay? So that is going to be 1 joule per 1 kilogram, right? So what is specific? Latent specific means basically unit mass, okay? This term specific means to unit mass, okay? And unit means 1, okay? That is 1 kg. So if I want to define this formally, so it is the energy required. It is the energy required. Energy required during melting. So what melting में क्या होता है? It changes from solid to liquid, right? During melting to change this state of 1 kg of mass at constant temperature, right? Okay, so this is basically the formula, and these are all the definitions of the variables which is in the formula, right? Okay, so this is for only melting point, right? If it is changing from solid to liquid. So does that make sense? If it is clear, give me a thumbs up. It's clear to Varda, okay. It's clear to Mema. What about Hamza? Clear हो गया. Varda clear हो गया. Me. What about Masha? Good, right? Mema, is it clear? Okay, good.
Yes.
Okay, so this is just basically now we have covered all the sections of graphs. ठीक है कि melting कैसे हो रही है, what are the points, melting point, boiling points, and what regions are basically the region where we had constant temperatures. So over there we have latent heat occurring, latent heat taking place, which is basically sort of game changes, right? Which is actually doing the work, right? At constant temperature. Okay. Similarly, following the same trends, then we have latent heat of vaporization. So just keeping this in mind, what do you think? What would be latent heat of vaporization? Yes, Vardha, what would you think? What is latent heat of vaporization? Vardha, are you here?
Sir, yes,
Mhm.
sir, I think latent heat is the heat that we need for vaporization,
Mhm.
and it is given out, I guess, when like you are boiling something,
Mhm.
and so it
Given out?
vaporizes, right? When
Okay.
I'm saying that when we boil something, it vaporizes, right? Like हम पानी को boil कर रहे हैं तो उसके water vapors बनते हैं. So I think the heat energy that is given out is latent heat.
Okay, so from this graph, so which section can the latent heat of vaporization is taking place? Tell me the sections. Is it A, B? Is it B, C? Is it C, D?
Sir, I would say it is CD.
Yeah, it's CD, right? Again, now you have two flat regions in this heating curve, that is AB and CD. Now AB can the okay, it is latent heat of fusion that is causing the state change from solid to liquid, right? At constant temperature. Now we have another constant temperature region that is CD, right? That is what they were interested, right? So it's pretty simple now. So if you want to just define it formally, that is going to be as follows. Okay, so let me just insert a page. Though now we have LV, right? Not, let me just get to it afterwards. First of all, let me define latent heat of vaporization. Latent heat of vaporization. For vaporization, it is converting into gas form, right? So now what is it, by the way? It is the energy required to change the state from liquid to gas at constant temperature, right? Okay. Now, what is the formula for this? This is pretty similar to the last one. It is equals to mLV, right? Subscript LV. So again, what is E here? What is M here? What is LV here? E is basically the energy required, and it is always in joules. And what is M here? M is again the mass of the liquid, right? That is measured in kilograms. And then what is LV here? LV is basically the latent heat of specific. It is the latent energy, right? Latent heat slash energy. And what is LV? It is specific latent heat of vaporization. V shows vaporization, right? And you apply this formula for only change of states when it is going from liquid to gas. If you are having a change of state from solid to liquid, you apply this formula. Okay. Make sure that you know when do you apply LF, when do you apply LV. These values are different. Okay. LF and LV differs. Okay. And it is measured in joule per kg. Again, if I ask you to define what is LV, that is going to be as follows. Okay. If I want to define LV, that is specific latent heat of vaporization. Okay, so this is basically, if you see the formula is this: E equals to mLV. If you make LV subject, it's going to be E over M, right? And specific always means unit mass, right? So if I want to define it in terms of words, it's going to be as follows. Okay, so it is the energy required. It is the energy required for a unit mass to convert the state from liquid to gas at constant temperatures. Okay. So what are the important points here? Let me highlight those. If you want to write down definition, let's say if you have a definition of 2 marks, so you should have this part. Okay, Ji, am I audible? Am I audible? Give me a thumbs up.
Yes, sir.
Okay, so if you want to basically have given a definition to write of 2 marks, so what should be there in your definition? So you should have this part, right? let me highlight it. You should have this part. Okay. From what to what? Let me highlight this and this part. Right. So if you don't have at constant temperature, you will lose some mark. Okay. Because from the change of state from liquid to gas is also called basically boiling or evaporation, right? So if you don't put at constant temperature, they would not count it as LV definition, right? Okay. And what is you have unit mass, you have change of state, you have constant temperature, right? Okay. So if it is clear till now, give me a thumbs up. So you have learned these things. It's clear to Varda, Momema, Hamza, and we are left with Mashal. Okay, that's good. So next we have, I can see this is invisible steam that is evaporating, right? Okay. Melting and solidification, we have learned this. Okay, so vaporization and condensation. Mm, this is important. Okay. So I'm going to leave this as your reading assignment. Okay, this slide. So this can be your homework. This is just a summary of what we've done. Homework, read on your own. Reading assignment. Okay, so this should be done before the next class. So now vaporization condensation. Okay, we had done this already. Let's skim it out. What is it? So if liquid particles are to overcome forces between holding them together and gain the freedom to move around independently as gas particles, they would need a large amount of energy, obviously. Okay. So this energy increases the potential energy of the particle, but not the kinetic energy. So energy is also required to push back the surrounding atmosphere in the large expansion that occurs when a liquid vaporizes. In the reverse process, the condensation which a vapor turns back to liquid, particles are closer together, potential energy is transferred from the particles to some energy to surrounding, right? So what is it saying? First of all, let me just show it to you. We have a boiling pan, right? इसको हम boil कर रहे हैं using a let's say candle. ठीक है, let's say we have a huge candle which can burn for a long time and we're basically sort of boiling the water, right? ठीक है जी. अब if I zoom in here and basically take the picture, you have particles here, right? You have particles here. ठीक है. Okay. So first of all, you have atmospheric pressure, right? You have atmospheric pressure, which is because of air. ठीक है. And then you also have within the particles that is called force of attraction, right? Force of attraction between neighboring particles and atoms. ठीक है. So if it want to basically break free from both of them, so these are the stopping materials, stopping sort of disturbances or hurdles for the particles to escape. ठीक है. So now they want to basically escape and go in air. ठीक है. So what they want to do? They want to basically first of all do what? They would have to basically break the force of attraction. ठीक है. Next thing which they want to basically utilize their work and basically energy for is overcoming the atmospheric pressure. Atmospheric pressure. Okay, that is caused by the air particles. If they can basically have enough energy to fight against the force of attraction and the atmospheric pressure, they basically break the bonds and they basically move freely away forever, right? That is how the change of state occurs. Okay, so that is they are saying here, you would have to provide energy to them. Okay, you would have to provide energy to them. And as you can see, their distance of separation has increased, okay, as compared to before. And if you basically recall your formula for gravitational potential energy, that was as follows. Okay, if you want to find gravitational potential energy, that is mg into h, right? So h is here the separation of between the neighboring particles. So the separation has increased. So you have basically provided them energy. Okay. Now, if you want to go in reverse, ठीक है, so surrounding से इसने basically energy absorb करी. Now, if you want to basically go in reverse, let me just choose another color. This one. If you want to go from this state to this state, okay. So what is happening now? You would have to basically not give an energy. So when they basically go back to the initial state, they give out energy, right? This is just conservation of energy principle. Okay, if you want to go from liquid to gas, you have to provide an energy. Okay, so that basically energy goes into surroundings. So if you're boiling water, if you keep your hands around the kettle or around the container, you would feel that your hands are getting warm, right? Because energy gets transferred to surrounding. If you go in reverse direction, let's say if you're washing your face in cold winters, and if you see a glass, so if you basically touch the glass, it's pretty cold, right? So energy is basically was transferred to surrounding, right? तो liquid की जो हमारे पास बन चुके हैं, so gas basically transferred energy to surroundings, and the glass becomes जहाँ पे liquid contain हो गया हमारे पास, that becomes cooler, right? So this is just explaining the process using energies. Okay, how does energy transfer takes place if you basically vaporize or if you do condensation, right? So if it makes sense, give me a thumbs up. I hope it is clear now. We know the definition now. We just basically take understanding here how is energy transfer taking place. So it's clear to Hamza, it's clear to Mema, Mashal, Varda, and Maeve is left. Maeve, any questions? Okay, good. So it's clear, right? नाउ बॉइलिंग एंड एवापोरेशन, ठीक है। सो जल्दी से मुझे अब आपको इस पे बात करनी है, दैट इज वेरी इंपॉर्टेंट कि पीपल आर कंफ्यूज है, बॉइलिंग एवापोरेशन सेम ही है, तो डिफरेंस क्या है दोनों, राइट? सो डिफरेंसेस बिटवीन बॉइलिंग एंड एवापोरेशन, ठीक है जी। सो लेट मी जस्ट मेक सम कॉलम्स हियर। सो वी हैव बॉइलिंग हियर, वी हैव एवापोरेशन हियर, ठीक है। सो कैन एनीवन give me any one difference between boiling and evaporation, right? Boiling में क्या हो रहा होता है? Liquid is also changing into gas, right? In evaporation, the same is happening. Liquid converting into gas. Sorry, liquid converting into gas in boiling also, and liquid converting into evaporation. Gas also in evaporation, right? Yes, so Mama. So can you highlight one difference between them?
Sir, like when we boil liquid,
Mm-hmm.
technically at a very high temperature, like 100 Celsius, it
Mm-hmm.
turns into gas,
Mm-hmm.
and evaporation form a floor, there is water, and it naturally evaporates by the sun. That's the
Perfect.
evap evaporation example
So
I remember.
good. So Mama is basically saying that evaporation can occur below the boiling point, right? Let's say if we take example of water, boiling point of water is 100 degrees Celsius. But if you have a pool, let's say pool of water after rain, so it evaporates, right, after some time. But in boiling, you observe it at a specific temperature, right? That is the boiling point, 100 degrees Celsius, right? Okay, so दोनों में काम एक ही हो रहा है कि it is converting into steam, right? Or gas. Any other difference if someone wants to chip in? Any other difference apart from this? Just imagine if you are boiling a water, okay, for let's say a cup of tea or a cup of coffee. Do you obtain the steam before it starts to boil? Does it occur to you? Have you ever noticed? I'm talking to the girls here, or the boys who also like to make tea, coffee for themselves. Have you observed this game? If you just start to heat it up, after let's say a few seconds, you start to see some steam over the container, right? But it hasn't achieved the boiling point, right? So these are the smaller minute differences which you should know, and it comes for 3 marks, 2 marks in exam. You just list out the difference between them. Okay, so you should know this. पहला difference क्या है हमारे पास in boiling and evaporation, which is shared by Mama. That is what K. But I'm just taking example of water here, right? Which has a boiling point of 100 degrees Celsius. ठीक है? So boiling basically occurs when boiling starts after the boiling point, right? So it is basically a fact that if you have crossed 100 degrees Celsius, then you will start basically to have a phenomena of boiling to start, right? So boiling point of water is there, 100 degrees Celsius. So after 100 degrees Celsius, if it crosses 100 degrees Celsius, then boiling will start. However, evaporation starts before the boiling point, right? It is very important. Then we have a second difference here. Okay, if you observed that boiling produces bubbles, right? If you are having a liquid that is boiling, you will have bubbles, which you have observed. Okay, I believe you all have observed. So evaporation, we have no bubbles. evaporation produces no bubbles. Produces no bubbles. All right. The third difference between this is basically boiling occurs. Boiling takes place in the entire liquid, right? If you basically see your kettle or let's say your water boiling, you would see bubbles are producing throughout the liquid. Okay. However, in evaporation takes place. Evaporation takes place only at the surface. Okay, if you have a puddle of water, so only the top, basically the layer. Let's say if you have a puddle of water like this, okay, only the top layer is basically have the particle which are have high enough energy to basically escape. Right, it is not occurring in the entire liquid in the entire pool of water equally. Right. Okay, जी. So what else is left here? What else do we have, which basically can dictate a difference between these two?
Water vapor and streams.
No, we have steam in both of them. Both of them produces steam. That is actually gas. What else can we have, which we are missing right now? Okay, so I would basically leave that for you to explore. Okay, so that is going to be another assignment. That is, I'm going to dictate here. So we have multiple slides. So we have. I would request you to skim over the slide before the next class. Just small questions. Okay, that is. Yes, Mama.
Or like boiling needs something to like
Hmm.
boil the water, but evaporation doesn't.
But evaporation also basically at least needs some energy to basically start evaporating it. So I would leave that to you for research. Okay, find out one more difference. It is a 1 mark, right? So now I'm going to deduct marks. If I haven't received any homework submission, simply cut your test marks. Okay. So you are just now not small kids. You should basically responsible. Okay. So I want the PDF submissions. Don't just send pictures because pictures are not easy to track. So I have a TA which basically maintains folders for submissions. ठीक है तो उसके लिए फिर पिक्चर्स को मेंटेन करना शुरू होता है. I always add the name at the top page. कि Mashal, if Mashal is submitting the homework, I just write Mashal name on the first page top, right? So now let's move on and let's see what does the slide says. Okay. So this is just a summary of what we have done till now. For pure liquid, boiling occurs at a definite temperature called its boiling temperature, right? And is accompanied by bubbles, ठीक है, containing gaseous or vapor form, ठीक है. Energy is needed for both, as Mama said कि सर boiling में energy चाहिए होती है, vibration होनी चाहिए होती है. That is wrong, ठीक है. We need energy in both of the processes, right? And it is basically stored in vapor form here. Okay. So when the vapor is cooled or compressed, it changes from liquid again. Okay. That is called basically condensation, right? So a few energetic particles close to the surface of a liquid may escape and become gas particles. So that is called basically evaporation. So that can occur at all temperatures. Okay. So we just need small enough energy to basically cause the energetic particles to basically escape, right? We have some chats here which I skipped. Sorry about that. So Mashal is saying that evaporation occurs at the surface of a liquid. That's good. Boiling happens throughout the liquid at a specific temperature. Perfect, Mashal. That's good. Sorry, I skipped your chat. I was basically not looking at the chat here. Okay. So yes, Mama.
Sir, I have a doubt that the difference I gave you. I
Mm-hmm.
understand that both boiling and evaporation needs energy, but like I meant to say, like the before some slides you gave an example of boiling that it needs like a gas burner or like some kind of machinery tool to like uh, boil the liquid up. Does evaporation also need kind of that?
Uh, I understand your point. You're trying to say कि sir for boiling you need a burner or a stove, ठीक है, or let's say some heater. But just imagine if you have a puddle of water, okay, sun is there, right? So sun is a source of energy which is giving it some heat energy, right? Sources are there in both of the formats. Okay, so this can be similarity in both of them. Okay, you need energy to basically start the process, right? If I ask about the similarities between the processes, तो वो क्या होंगी हमारे पास? What are the similarities? If I ask,
They
explain.
both occur in liquid and
The,
they both need some sort of heat energy to
yeah,
work.
they both basically causes the change of state from liquid to gas, and they both need energy to basically start the process. Okay, that's good. So you should keep them in mind. Okay, don't just certify the definitions. Okay, so now, okay, so just imagine that's the last thing which I want to cover. Then I will do from here in the next class. Then I will do some question answers. Okay, I'm going to draw a picture here. Okay, so just to have some graphs. Okay, so you have a land here. Okay, let's say you have the land here, and you have some puddle of water here, right? Okay, so okay, so you have a puddle of water here. Okay, and let's say this is Umama standing here just to observe the physics laws and principles told by Sir Khuzaima. Okay, she want to verify that is it correct or not. And you have basically sun here, right? Have sun here, right? So let's say the temperature goes from 25 degrees Celsius to 35 degrees Celsius. Okay, after some minutes, after some hours. Okay, so what would you observe here? So you would observe that as the temperature starts to increase, you would see that the puddle of water, let's say it was 10 a.m. in the morning here, and this is 5 p.m. at the noon, right? So if you come, let's say, visited the puddle of water after 10 a.m. to 5 p.m., okay, you would have observed that the puddle might have shrinked, right? This would go from this size to this size, right? So it almost shrink to half, okay? Now let's say similarly there was a magic, okay, and it almost went to 45 degrees Celsius, okay, at 7 p.m. Let's say there is no sunset, okay, we are living in parallel universe. Then basically, I made the adjustment over here, okay. Now the puddle is almost this, okay, so almost ये one third हो गया. So can you basically just analyze this effect? What is the rate of evaporation here, and what is the rate of evaporation here? Has it increased or decreased? Rate means ke it is how much of water is basically converting into gas as compared to time, right? Rate means this, right? So has it increased or decreased? Rate of evaporation क्या है हमारे पास? Is basically evaporation is conversion to gas as compared to time. So has it increased or decreased? If you are saying yes, if it is increased, raise your hands. Omega says case it has increased, the rate of evaporation has increased. But they also say that what about the rest? Okay, Hamza also say Mashal also says that have you noticed that rate of evaporation बढ़ रहा है as temperature increases? Okay, yeah, that is correct, right? So as the temperature is increasing, the rate of evaporation also increases, right? This is one factor which basically leads to high rate of evaporation. Okay, so similarly, if I basically say that there is wind flowing, right? The wind started to blow at a very fast rate, right? So now let's say after 10 a.m. she came at let's say 2 p.m. Okay, this is day two, and she basically see that at this instant of time that is 5. Let me just fix the time. Okay, 5 p.m. So again the puddle now becomes this, right? It almost shrinks. Okay, so if you compare this and this, it has reduced. Okay, so if you basically also increase the wind, so increasing wind can also increase the rate of evaporation, right? Rate means कि कितनी जल्दी से हो रहा है, how fast it is, right? We have now discovered two factors here, ठीक है? That is temperature, that is flow event, right? Okay. Now last thing which I want to say कि if you have a puddle which is basically pretty flat, right, like this, and the ground between the ground below this is only, let's say, of 1 meter, and if you compare this with a puddle which is basically pretty thick in depth wise, ठीक है, and it has a depth of 5 meters, which one would basically evaporate slowly and which one would evaporate fast? Yes, Vardha.
Sir, the one with depth of 1 meter.
Yeah, ठीक है, this is case C. तो if you basically have greater surface area, ठीक है, greater surface area, so that would also basically increase your rate, right? Surface area means के कितना water expose हुआ है, ठीक है, as to the sun or to the environment, ठीक है. Now we have three factors which can basically lead to high rate of evaporation. That is what is written over here, right? So the temperature is higher, ठीक है, the temperature affects the rate of evaporation, the surface area of the liquid, ठीक है, and the event, ठीक है. And how does it affect? So if you have high temperature, you will have high energy transfer to the particles. Therefore, they can easily overcome the forces of attraction between each other and the atmospheric pressure, and they can escape easily, right? If you have greater surface area, so you have more particles exposed to the environment, hence they will basically escape. Okay. If you have a greater wind, so they will basically take away the high speed energy particles with themselves, ठीक है, so they can basically help away to, they can also provide a sort of a force, ठीक है. If you have a puddle and if there is a wind here, ठीक है, so they can, let's say this is particle P here, so if they sort of basically give it a push to basically escape, right? So that's how they can also help to increase the rate of evaporation, right? So that are the three factors which are important and which comes in your quizzes, MCQs, and exam. To basically just, if they can ask you to list it out, they can ask you as a MCQ, okay, if there is a windy day as compared to a day where there is no wind, so at what, let's say you have a puddle, so when would it basically be shallower, right? Okay, so these are the things which you want to keep in mind.